In this video, we'll learn to read, write, order and compare positive and negative numbers of any size. In a previous video, I've looked at reading, writing, ordering and comparing positive numbers up to 1 million. So if you're unsure about your skill at that level, go and revisit my level 1 video. Whereas here, we'll work on numbers that are bigger than 1 million. So the number that I've written here is read as 1,111,111. So what would happen now if I add a digit here? If that digit is 1, how would I read this? As you can see, there is a pattern. I'm grouping these digits into 3. So here is more or less the same thing that would happen in the second digit of the group of 3, here and there and so on. So have a look at that. What is this digit? That is the tens. And what's that one here? That's the tens of thousands. So this is going to be tens of millions. So I'd read this as 11,111,111. So this here would be 25,105,055. So we read them in groups of 3. So what happened now if I add another digit? So let's say I'll make this as following the pattern again, units, tens, hundreds. So I've got millions, 10 millions, 100 millions. So 405,426,456. That's how we read this number. So something very similar to this, then you'd be this would be read as 599,040,500. So we separate them to help us read the numbers in blocks of 3. So it's time now, if I add another digit, to put another comma in there. So let's say I have this number. So we're finished with the millions now. What comes next? It is the billions. So this here will be the billions column. So I've got 1,052,483,050. So another one. So this one is read as 4 billion. So that comma here helps me read it. I can see it's after the million, so it must be, or in front of the million, so it must be billions. So they come into the units and then the thousands. There we got the millions and then the billions. So again, that's a billion, then it would be the 10 billions, then it would be the 100 billions, and then a comma again, and we'd have trillions, so tens of trillions, hundreds of trillions, then quadrillions and so on. So if you're interested, you could have a look online as well. So how I read this number would be 4,005,834,056. And let's take this one. So again, separating them would help me. So I'd go 1, 2, 3 digits, put a comma in there, 1, 2, 3, comma, and so on. And we've learned that a million has 6 digits after, or 6 zeros. So I'll know that this is the units, tens and hundreds, and then going on to the thousands, millions, so this must be the billions. So I'll start with the billions and say 145 billion, 83 million, 461,234. So commas are really important. And then after this, as we said, would come the trillions, so 3 digits for the trillions, and then 3 digits for quadrillions, and so on. So I've written and read these numbers. In terms of ordering them, obviously you can see that this come in order from smallest to the biggest. So first of all, you see which of these numbers has most of the digits, and the more digits it has, the bigger the number it is. So this one has most of the digits, so it's got to be the biggest one, because as we said, this would be 145 billion, whereas this one is just 4 billion. So of course this is bigger, and that's the case when you compare this with this, for example. So that'd be 25 million, whereas this is 405 million. So the more digits, the bigger the number. And then for those that have the same number of digits, like these two, for example, then we'll look at the first digit. If that is bigger, the whole number is bigger. Because look at this. This is 405 million, whereas this is 599 million. And then if that first digit is the same, so let's say I'll change this into a 4. So this is now a 4 as well. So 405 million, and this is 499 million. So what matters then is the next digit. And let's say this is a 9 as well. So if we have both 9s, then we look at the next one, because that makes most of the difference. This would be 495, and this would be 499 million. So it's the next digit. And if that's still the same, you look at the next one. If that's the same, till you come to a point where you look at the last digit, and that is what makes the least of the difference. So then we can say, of course, this number is bigger than this number is bigger than this number is bigger than that, and this is bigger than them all. So if I were to order them, this would be coming first, second, third, fourth, fifth, sixth, and seventh. In terms of negative numbers, we could benefit from referring to a number line or a thermometer. So if this is 0, this is going to be 1, 2, 3, 4, 5, 6, and so on. And then we go down to -1, like temperature. If it goes down, that means it's a smaller value. Or if you are overdraft, that means you've got less money. So if you go this way, always the numbers get smaller. So going down in this number line means numbers get smaller. So -2 and -3, -4. So you'd be much colder when the temperature is -4 than when it is actually 3 degrees or 0 degrees. So with a minus in front, the numbers will get smaller. So -4 and -3, which one is smaller and which one is bigger? -4 actually is smaller because it means having less money, it means a lower temperature. So despite the fact that this is a digit 4 and this is a digit 3, minus that minus in front makes it even smaller. So -4 is smaller than -3, smaller than -2, smaller than -1, 0, and so on. So I'll place some minus or negative signs in front of these some of these numbers so that we can actually order and compare them. So I've placed this minus sign in front of this number, and this one. So now I'd like to order all of these numbers all together. So let's start ordering them from the biggest to the smallest. So which one would be the biggest? When we compared them, we looked at all positive numbers. Now we have positive and negative numbers. And as we looked at this one, we said that positive numbers are always bigger. So I know that this, and this number will be bigger than the ones with the negative signs in front. So it's okay to find the biggest number of them all. It's a case of comparing these 4 positive numbers first. And as you can see, this one has more digits than these have, so it's got to be the biggest number of them all. So 145,083,461,234. So that's the biggest one. Then out of them 3, this one is the next biggest one because it has more digits than the other 2. And this comes next, and that's the 4. So I dealt with the positive numbers first because positive numbers are always bigger than negative ones. Now we'll look at the negative numbers. When we looked at these, we said that the number that has the smaller digits will be the biggest one. So this time we're reversing the process. If we look at these 3, I'm not looking for the one that has most of the digits, but I'm looking for the one that has the fewest digits. So this will be the next biggest one, because being overdraft by 25,105,055 pounds is not the same, or is less than being overdraft by 499,040,500. So this is better, this is a bigger number. So that must be the next one, the 5th one. And then will come this one because it has more digits than this, but it has fewer digits than this one. So that is number 6, so the 6th one. And finally, it's this number here, which we read as -4,5,834,056. So for negative numbers, we reverse the process when we find the biggest number. We're looking at the smallest digit or the number with the fewest digits. In this video, we'll learn to carry out calculations with numbers up to 1 million, including strategies to check answers, including estimation and approximation. So we'll start with addition, then we'll do subtraction, multiplication, and finally division. So we start by lining up the numbers correctly, meaning that digits with the same value are under each other. So units under the units, tens under the tens, hundreds under the hundreds, and so on. So we start adding from the right. So adding up the units, because if we have anything to carry over, we can do so to the tens and then to the hundreds and so on. So 3 and 0 and 1 makes 4. 8 and 6 makes 14. And the 4 makes 18. So 8 down and the tens are carried over. 6 and 1 is 7, and 7 makes 14. So 4 down and 1 carried over. 1 and 1 is 2, and 2 is 4. 4 and 8 makes 12, and a 5 makes 17. So 7 and 1 carried over. And 1 and 4 makes 5. 5 and 8 makes 13. So the answer is 1,374,484. So how can we check that this answer is correct? There are different ways we can do this, and one of them is by subtracting. So maybe subtracting one of these amounts to see whether the remainder adds up to the total of these two, or subtracting one of these, or maybe adding these two first, working out the total, and then adding this on top. So we could repeat the calculation, but we could also use estimation and approximation. So if I round this to 41,000, so we round them to the nearest thousand. So the first one is 41,000. The second number is 482,000. The third number is 852,000. And the way we round them is by looking at the digits next to them. So that's a 0, but this is a 6, so that's going to make it to 1. So round this up, and that's a 7, so it's going to round this to 2. That's a 0, so there is no change with a 2 there. If you need to recap estimation and approximation, have a look at the videos that link to this. So adding these up now, got 0, 0, 0, 5, 9 and 8 makes 17, so 7 and 1, and there we have 8, 9, and the 4, 13. So this is 1,375,000, which is very close to the answer we had there, suggesting that we've got it right the first time round. Now moving on to subtraction. Again, line them up correctly, units under the units, tens under the tens, and so on. And we start with a unit. So 9 take away 4 leaves us with 5. 1 take away 1 is 0. 0 take away 4 gives us a negative number, so we'd have to borrow 1 from the 4 to make it a 3, and this becomes a 10. 10 take away 4 is 6. 3 take away 8 gives us a negative number, so I'll borrow 1 from this, and this becomes 13. 13 take away 8 gives us 5, and 2 take away 5 gives us again a negative number, so I'll borrow 1 from the 6. 12 take away 5 gives us 7. 6 take away 5 gives us 1. So the answer is 175,605. So that's pretty much similar to the fraction of numbers that are smaller as well. So nothing has changed, we just have more digits. And same thing with addition as well. The same procedure, it's just the number of digits that we have more here of has changed, nothing else. So now we'll check using estimation. You could also add these two up to see whether it gives us a total. So that's another way. You could repeat the calculation again to see whether that gives us the same answer. Whereas I will round it, so I'll estimate what the answer is and see whether that matches. So I will go maybe rounding to the nearest 10,000 this time. So it was 734,000, so it's going to be 730,000 minus 560,000 because of the 8 there. I could have rounded to the nearest 100,000, could have rounded to the nearest 1,000 as well. so it does not really matter. If you round to the nearest thousand though, it's like to give you a more accurate answer. But you don't want to overdo it. You don't want to round to the nearest 100 or 10 in this case, because then that would be very close to this and there is no point in estimating and approximating. So we've got 0, 0, 0, 0. 3 take away 6 gives us negative, so we're going to borrow 1. So this becomes 13, take away 6 gives us 7. 6 take away 5 gives us 1. So it's 170,000, which is very close to 175,605 that we had when we worked it out. Now we'll look at multiplication. So the same procedures will follow as if we had fewer digits. So we will go starting with the units. 5 times 6 is 30, so 0 down and 3 carried over. 5 times 5 is 25, and the 3 is 28, so 8 down and 2 carried over. 5 times 7 is 35, and the 2 is 37. 5 times 2 is 10, and the 3 is 13. 5 times 9 is 45, and the one that we had, 46. 5 times 4 is 20, and the 4 is 24. So we're finished with the 5, now we'll move to the 9. The value of the 9 is 90, and for that reason we'll put a 0 down and multiply all these digits by 9, because that's a nice and easy way to multiply by tens. So put the 0 down and then treat it as if it was a unit. So 9 times 6 is 54, so 4 down and 5 carried over. 9 times 5 is 45, and the 5 is 50, so 0 and 5 carried over. 9 times 7 is 63, and the 5 is 68. 9 times 2 is 18, and the 6 is 24. 9 times 9 is 81, and the 2 is 83. 9 times 4 is 36, and the 8, 44. So we're finished with the 9 as well. Now we're looking at the 4, which has a value of 400 in fact, because it's 495. So now this time we'll put 2 zeros underneath, and we'll treat this as a unit. So 4 times 6 is 24, so 4 down and 2 carried over. 4 times 5 is 20, and the 2 is 22, so 2 and 2 carried over. 4 times 7 is 28, and the 2 is 30. 4 times 2 is 8, and the 3 is 11. 4 times 9 is 36, and the 1 is 37. 4 times 4 is 16, and the 3 is 19. So we've got all of these. We'll now add them up. So 0, 8 and 4 is 12, so 2 down and 1 carried over. 7 and 4 is 11, and 1 is 12. 8 and 2 is 10, 13 and 1 is 14. 6 and 4 is 10, and the 1 is 11. 7, 8, 9. 11, 13. 9 and 1 is 10, and the 4 is 14. 1 and 1 is 2. So the answer is 243,914,220. So I'll try to round this off now. 492,756 I'll round that to 500,000. And we'll multiply that by 500 because it's 495, so very close to 500. But I could have multiplied maybe 493,000 by 500, so that is possible as well. And the easy way to do this is multiply 5 by 5, which is 25, and then add all these zeros. So 1, 2, 3, 4, 5, 6, 7. 7 zeros. So 1, 3, 4, 5, 6, 7. And what's this number? Let's separate them. 3 and then 3. So it's 250 million. And if we compare it to this, which was 243 million about, that, or 244 million, if we consider the 9 there, that is very close to it, suggesting that we got the calculation right. Now we'll do the division. So we'll do 8, 4, 6, 1, 4, 2 divided by 14. So we'll start by looking at how many 14s fit into 84, and it is 6 of them. So then we'll look at how many is 14 lots of 6. It gives us exactly 84. So we haven't got anything to carry over, so we can cross these out and look at the 6. So how many 14s fit into 6? And that is 0. And 0 lots of 14 means 0, so we have to carry over the 6, so that makes it 61. So then we look at how many 14s fit into 61, and that is 4. So 14 lots of 4, or 4 lots of 14, makes 56. So that means 56, we've got 5 remaining from the 61. So now we look at how many 4s would fit into 54, and that is 3 of them, because 14 times 3 gives us 42. So taking that 42 away from the 54, that gives us 12. So we've got now 122. So how many 14s would fit into 122? You can add up to get to a point where you see that there are 8 of them, because 14 times 8 gives us 112. So there is 10 remaining. Now at this point we're finished with the whole number, and that's where we put a decimal point here. And we can add as many zeros as we like after this point, after we put the decimal point. Some people like to put a decimal point here as well, and that's perfectly fine. Now we're looking at how many 14s fit into 100, and it is 7 of them, because 7 lots of 14 give us 98. So there'll be 2 remaining, so we can add zeros again now. There is no problem because we've got a decimal point, and zeros after a decimal point, we've said, don't make any difference, they have no value. So how many 14s into 20? That's just 1 of them, and we'd have 6 remaining, so this becomes 60. How many 14s into 60? And that is 4 of them. Now as you can see, this is not ending, and we could continue for a long time with this decimal. However, if we've got 3 decimal places, which means 3 digits after the decimal point, then we're pretty much there, so we don't need to continue this forever, and we can stop here. So our answer would be 60,438.714. So you could round up these answers to try and see whether they fit like things like 90,000 divided by 15, and it gives about 60,000. Or you could round this up and multiply it by this to see whether they give you this total. So if this is maybe 60,000 multiplied by 15, so six lots of 15, let's do 2 lots, which gives us 30, and another 30, 4 lots, and another 30 gives us 6 lots, so that's 90. So we've done these two. Now we add these zeros, so 1, 2, 3, 4, so 900,000, which is roughly about the answer that we initially had, which is 846,142. So we've estimated this as well, and another way to check this answer could have been to really divide this big answer with 495 or divide it by 500 and see if it gives you something close to that. So that's just another way of checking the answer. So we've looked at these different calculations. We've looked at adding, subtracting, multiplying, dividing, the strategies to check answers, including using estimation and approximation. In this video, we'll learn to evaluate expressions and make substitutions in given formula, in words and symbols. So we'll start with expressions. And I've given 2 examples of them in words. So the first one is, when hiring a taxi from ABC Taxis, you pay £2 per each mile you're travelling and a £1 booking fee. How much would you pay if you travelled 6.2 miles? So if you travelled 6.2 miles, that means that you'd have to pay £2 per each mile, so that is 6.2 times 2, and then add a £1 booking fee on top of that. So 6.2 times 2, or 2 times 6.2, because that's easier to do, that would give us 12.4. Add the 1, which is booking fee, that gives us in total £13.40. So we've worked it out, and that means we've actually evaluated an expression given in words. But what would this be like if we had it in symbols? So we'd write 2, so that's £2, so write 2 per each mile, so 2 times m, but a shorter way to write it would be just 2m, because in maths, when you have multiplication and it's letters and numbers mixed together, you don't need to write the multiplication symbol, because it can be confusing as it looks like an X. So 2 lots of m, so miles multiplied by 2 plus 1. So we'd do the same thing, we'd work it out by replacing m with 6.2 miles. So 2 lots of 6.2 plus 1, and that gives us 13.4, or £13.40. So if it was 5 miles, then it would be 5 times 2, 10, plus 1, 11 pounds. Now let's look at another example. In a shop, a banana costs 6p and an apple costs 5p. How much would you have to pay for 8 bananas and 7 apples? So again, we're looking at 8 bananas and each of them costs 6p, so I'll do 8 times 6, and then we'll add to it 7 times 5, because there are 7 apples and they cost 5p each. So that means 8 times 6, which is 48, and 7 times 5, which is 35. So what we're going to do now, add these together. Notice how I did the multiplication first and then added these two amounts together, BIDMAS. So 40 and 30 is 70, 8 and 5 is 13, 70 and 13 is 83. So 83 what? What's the unit? We input pence in both cases, so our answer will be in pence. How this look like in symbols? So again, what did we multiply? It was 6p, so 6 for each banana, so you could say 6b, 6 lots of b, 6 multiplied by b. Add to it 5 times 7, but we don't, 5 times 7 apples was specifically, but we don't need to write the number of apples and we don't need to write the multiplication sign, so I'll just write 5a, because in this way I can input any number of bananas or apples and still get the answer for the total cost. So in this case we replaced b with 8, so 8 bananas, and apple with 7, so that gave us 83p. But it could be, let's say, 5 bananas, so 5 times 6, 30, and 6 apples, 6 times 5, 30 again, so 60p in total. So you can have any number of apples or bananas. So as you can see, expressions look like different terms together. So this is one term where we've got numbers and letters, and then we have added 1 to it, so that's another term. And if you look at this one, we've got 6b, so a number and a letter, and then a number and a letter. So typically this is how they look like. There is no equation sign for or symbol for expressions because they're not equations, they're not formula. That is how expressions look like this or like that, or you could have 1 first, 1 plus 2m, but this is how they look like typically. In this video we'll learn to evaluate expressions and make substitutions in given formula in words. So we've got the formula given to us in words. So the first one says to find the area of a rectangle you multiply the length by the width. Would be the area of a rectangle which is 13 centimeters long and 5 centimeters wide. So we're working out the area and it says to multiply. So we go 13 times 5, that gives us 65. We input centimeters, and since we're working out the area, this must be squared. Now to write this in symbols, we worked out the area of a rectangle, which is equal to length, so L to represent length, times W to represent width. The next question is saying, to convert a temperature reading from degrees Celsius to degree Fahrenheit, you multiply the temperature in degrees Celsius by 9 divided by 5 and then add 32. What is 15 degrees Celsius in degrees Fahrenheit? So we've got to get the temperature in degrees Celsius, which is 15. So 15, then multiply the temperature by 9 over 5 and then add 32. So we do that in a calculator. 15 times 9 over 5, add 32, gives us 59. 59 degrees Fahrenheit, that is. So to write this in simples, we go, that's what we're looking to work out, degrees Fahrenheit is equal to the temperature in degrees Celsius times 9 over 5 plus 32. We shouldn't forget that we multiply first before we add. In this video, we'll learn to identify and know the equivalence between fractions, decimals and percentages. There are main fractions, decimals and percentages such as 10%, which you should know as a fraction, as well as a decimal, 25%, 12.5%, 50, 75, 80%, 60 and so on. So what I'll try and do is show how to convert between a fraction to a decimal and percentage, between decimals, fractions and percentages, and between percentages to fractions and decimals, so that you can work with any of these fractions, decimals and percentages, not just the common ones. So I'll start with fractions. So let's say if I have 3/8, for example, and I want to convert it to a decimal or to a percentage. If I want to convert it to a decimal, all I have to do is 3 divided by 8. As I've shown before, that line in the middle means division, and it's like the division sign in a calculator. So there is a number at the top divided by the number at the bottom. This is the bottom that represents it. So I would go 3 divided by 8 because it's 3 out of 8 and it means the same thing. So 3 divided by 8 equals, that gives me a decimal, so 0.375. So I've converted it to a decimal. All I did was divide 3 by 8. Now if I want it as a percentage, so we've related this to money before, and I like to relate it to money again. So if I was given this amount with a pound sign in front, I would see that I'd have 37 pence and half a penny. So that is pence, 37 pence, because pence is out of 100, which makes a pound. It's the same thing, pence and percentage. So this is 37.5%. So pence and percent. But also, if you like working it out, you could just multiply it by 100 and it gives you the same number. So, but the easiest way to do it, just by looking at this, okay, the 2 digits after show me how many pence there are when you look at money. So that would be 37.5%. So the same thing would be really applicable if you had any other fractions. So I will try out another one. Let's say 7 out of 25. So 7 divided by 25. 7 divided by 25. And you could do this division by hand if you didn't have a calculator. So that is 0.28. So I've got it as a decimal already. And then we said 2 digits after the decimal point. So that is 28%. It's like 28 pence in a pound. If we have, so we've converted fractions to decimals and to percentages. So if I was asked to convert a fraction to percentage, I would go through having it as a decimal first and then into a percentage. If I just wanted a decimal, so a fraction to a decimal, just divide it and have it like this, or this. Now, if we have a decimal, how do we turn it into a fraction or percentage? If I have a decimal, let's say 0.35, what is this as a percentage? As a percentage is very easy to work out because we've got 0.35 as I said, 2 decimal places, and we get 35%. It's like 35 pence. If we want to convert it into a fraction, so 0.35, it is, as I said, 35 pence in a pound, so 35 pence out of 100. So you could have it like this, or you could simplify it further, because this can actually be simplified. And 5 is a number that goes into both of them. So 35 divided by 5 gives us 7, and 100 divided by 5 gives us 20. Now at this point we can't go any further, so we've got to leave it as 7 over 20, or 7/20. And the same thing if I picked 0.125, for example, this is going to be 12.5%. And if I convert it into a fraction, it is now not 125 over 100, but it's 125 over 1,000. So look at the digits, there are 3, so the number underneath needs to have the same number of zeros. So look at that, 2 digits, 2 zeros. It's a bit like having 125 milliliters in a liter. So that is what is happening here. And again, now 125 over 1,000, we could simplify this further, and immediately I can see that 5 is a number that go into both of them, because multiples of 5, or numbers that can be multiplied by 5, would have an answer of ending in 5 or 0. So if I divide this by 5, that would be into 10 would go 2 of them, and we'd have 2 remaining. Then into 25, that would be 5 of them. Now trying to fit 5s into 1,000, that would be 200 of them. So that means we can still simplify this. And then again, 5 could go into both of them. So this would be a 5. And if I divide this by 5, it's going to give me 40. So again, we can divide by 5. So that's going to be 1. And this is going to be 8. So when it comes to percentages then, let's say we have 4%, and we'll convert this into decimal and fraction. So to convert it into a decimal, it's very easy, because it's, as I said, 4% is like 4 pence. How do you write 4 pence? And I would write this like that. So imagine a pound sign in front. And to write this as a fraction, so 4%, as I said, percent means out of 100, so that is 4 out of 100. So this is a fraction already, but if you want to simplify it further, then I can see that I can divide this both by 4, so that's going to be a 1, because 4 divided by 4 gives me 1. 100 divided by 4 gives me 25, so 1 over 25. Let's try another one. So let's say if we have maybe 150%, so maybe an increase from 100%, half added on top. So now 150 pence, how do you write that with money notation? That would be 1.50 50 or just 1.5. So that's this as a decimal, and 150% as a fraction, it would be 150. We said percent means out of 100, so 150 out of 100. Now I can divide this both by 10, so it's going to be 15 out of 10, and I can divide them by 5, so this would be 3/2. So 3/2 would be the fraction that represents 150%. So we've looked at how to convert fractions into decimals and percentages. We looked at how to convert decimals into percentages and fractions, simplified fractions as well, not just fractions, because we had them originally into these fractions and then we simplified them most of the time. And we had then percentages which we turned into decimals and fractions. So through this then you can identify and know the equivalence between fractions, decimals and percentages. In this video we'll learn to work out percentages of amounts and express one amount as a percentage of another. So we'll start first with working out percentages of amounts. I've represented here 60% of 58. As you can see, I've split 58 into 10 equal parts and I've highlighted 6 of them because that represents 60% of 58 in this case. So one way to work this out would be to divide 58 by 10, so we get 10%, and then multiply it by 6, so we get in total 60%. So that's one way. So 58 divided by 10, which would give us 5.8, and then go and multiply 5.8 by 6, which is 34.8. So that is 60% of 58. This is one way of working out. Another way of working it out would be to divide 58 by 100, so we get a tiny amount, 1%, and then multiply it by 60. So 58 divided by 100 gives us 0.58, and then we multiply it by 60 to make it to 60%. So 0.58 times 60 gives us 34.8. So it gives us the same answer. Now another way of working it out, because there are many different ways, would be to go, right, 60%, I want to work out 60%. So 60% means 60 out of 100. So I'll go 60 out of 100 off 58. So off means multiplication. So 60 divided by 100 times 58. And that again gives us 34.8. So that's another way. Again, 60% is 60 out of 100, which is 60 divided by 100 of 58 multiplied by 58. And very closely linked to this is another way of working this out, because 60 out of 100, we should know it's 60%, and as a decimal we write it 0.6 or 0.60, and then going back to this, multiplied by 58. So this is a good calculator method, and it gives us 34.8 again. So all these methods give us the same answer. So these are some different methods of working out, and there are definitely more methods than these. And I'm showing these to you so that you can pick the method that you like to use yourself. So now we'll pick another example just to illustrate. So let's say we want to work out 32% of 152. So again, 32%, let's follow this method. So we said we divide it by 10 first, so we find 10%. So 152 divided by 10 gives us 15.2. So we've got 10%. Now we'll get 30 by multiplying this by 3. So 15.2 times 3, that is 45.6. So I've got 30%. Now I just need 2%. So if I find 1%, I can double it and add it on top of this. So 1% will be found by dividing this by 100. So that's a very tiny amount there. So 152 divided by 100, that gives 1.52. And I need another lot of 1.52 to make 2%. So that is 4, and that is 10, so 3.04, which I need to 3.04 needed to add to the 30%, which was 45.6. So added these together, then we get 48.64. So this is a good mental method. If you have a calculator, if you can use a calculator, then definitely it's good to know this method, but not the easiest to work out when you have a calculator. So definitely a mental method. Now the other one was this, which is more like a calculator method. So we said the total we divide by 100 and then we multiply by how many percent we want. So I would go now 152 divided by 100, so that gives me 1%, which is 1.52, and then get that 1.52 and multiply it by 32, because I want 32%, times 32. So 1.52 times 32 should give us the same answer as what we had before, so it is 48.64. So we've got the second method. Now we'll try this one here. So we said we want 32%, so that's 32 out of 100 of 152, so times 152. So that straight away gives us the answer, which is 48.64. And linked to this was the other method where we know straight away that 32 divided by 100 is 0.32 times 152 gives us 48.64. So this has explored quite a few methods. We've got 1, 2, 3, 4 methods of working out percentages of amounts. Now let's express these amounts as a percentage of 58 and 152. So let's take the first example first. So it was 34.8 out of 58. So we write that as 34.8 out of 58. What does that give me? 34.8, sorry, divided by 58, that gives us 0.6. So can you see that link now? That's the decimal, and to turn it into a percentage, we've said we look at the 2 digits after the decimal point. So this is 60%, and it matches exactly what we had to begin with. So 34.8 out of 58 is 60% of 58. And the other example, we had the amount was 48 48.64. So 48.64 out of 152. And we've said that line means division. So I'll go 48.64 divided by 152. That gives me 0.32. So that is the decimal. How do we turn that into a percentage? We look at the two digits after the decimal point. So that is 32%. And that is exactly what we had to begin with. So we worked out 32% of 152. That was 48.64. Now we're reversing the process. We had 48.64 out of the total 152, which gave us 32%. So to work out one amount or express one amount as a percentage of another, get that amount out of the total or the other amount, which means we're dividing, and then you get the decimal. Through the decimal, you move to the percentage, just like in the examples given here. In this video, we'll learn to calculate percentage change, any size increase and decrease, and then work out original value after percentage change. So we'll start with calculating percentage change first. What is percentage change? I've given two examples here. One is an increase and the other is a decrease. So let's suppose that the original price of a coat was £50 or a pair of shoes, whatever you might think of. Then that price goes up to £74. So what is the percentage change? One thing that I want us to bear in mind is that this is the extra amount, and that extra amount is a percentage of the £50. So this same amount could have been here at the beginning, anywhere in the middle. So it's taken or considered to be part of the 50 and added on top. So what do I mean by that? This is £24 extra, because 74 take away 50 gives me 24. So it is 24 extra, which I could have had here, there in the middle, or at the end. So it's 24 out of 50, because that's the original amount. That's the 100% amount as well. So we always say 24 out of 50, the difference out of the original. So 24 divided by 50 gives 0.48. So what's that as a percentage? It is 48%. So the percentage increase in this case is 48. That's the percentage change as well. So it means the same thing. Now, what's happened is that here we have another scenario. So a pair of shoes costing £50, then it decreased. It went down to £42. So it's not 50 anymore, but it's 42. So what is that percentage change? We see it's changed, it's gone down. How much has it gone down by? It's gone by £8. Now £8, we're trying to work out what is this as a percentage of the 50. So 8 out of 50, always looking at the one that matches 100% or the original value. So 8 out of 50, or 8 divided by 50, gives 0.16. So that as a percentage is 2 digits after the decimal point, 16%. So the percentage change here is 16%. So percentage change, either increase or decrease, is worked out by finding what is the difference between the two values. So that was an increase, £74. What was the original price? It was 50. So what's the difference between them two? It was 24 out of the original price. And that means, of course, turn it into a decimal, because this line here means division. So 24 divided by 50 is 0.48, and that is 48%. Just like 48 pence would be notated with a pound sign in front. And now we have here a decrease. So it went from 50 to 42. What was the change? It was £8. So 8 out of the original, which was 50, 8 over 50, or 8 divided by 50, gives us 0.16. Again, that means 16%. Now we'll look at working out the original value after percentage change. So let's suppose we've been given that the new price of a pair of shoes is £74, but we don't know what it was originally. And we are given that there's been an increase by 48%. So we'll need to find what was that original value, or the 100% value before the increase. So if we add 48% to the 100 that we had already, 100%, that is going to become in total 148%, because there is an increase in there. And that 148% is equal to £74. What we need to know is what was the value at 100%. So what this means is that rather than splitting the number by 100 to get 1%, now we've got to split that 74 by 148 in order to get 1%, because we've got more of it. We've got 100 and then 48 as well. So in total, that is 148. So that's why I'm going to divide 74 by 148 to get 1%. One tiny amount, which could be here, could be there, anywhere, is the same. It is the same. So 1%. So I'll go 74 divided by 148 gives me 0.5. So 1% is 50 pence, in other words. Now I've got 1%, but what am I interested in? I'm interested in 100%. So then I'm going to multiply 0.5 by 100, which gives me 50. So that's given me the 100%, which is this value here. So it is £50, which is what we started off with anyway. So we've worked it out. Now we'll do the same with the decrease. So let's suppose we know that the new price of a pair of shoes is 42, but what was the original price? So we don't know anything that we've worked out here. We know that there's been a decrease by 16%, so this must be equal to 84%. This point here, 42 must be equal to 84%, because we've decreased this by 16%, because you'd be given the percentage. If you're not given the original value, you'd be given what percentage it's gone by or down. up or down. So what I will do is exactly the same thing that I did there. £42 is 84%. So in order to get 1%, I'll divide this by 84. So that's going to give me one small slice, 1%. So 42 divided by 84. That gives me 0.5. So 50 pence is 1%. So 0.5 now, I need to work out 100%. So I'm going to multiply it by 100 to give me 50. So that's given me £50 for it. So what we did now was trying to represent the new value. If it's increase, show it as an increase. What is the price? How many percent does it represent? And if it's an increase, it's going to be more than 100%, because the original value is 100%. And then take that new value, divide it by how many percent there are in total. That's what we did. And that gives you 1%. That 1% then scale it up or multiply it by 100 to give you the original value. And exactly the same thing over here. We looked at what is the new price, how many percent does that represent? So divided, so new price over the percentage that it represents, and that gave us how much 1% is, and then again multiply by 100 to give us the original or the 100% value. In this video, we'll learn to order, add, subtract and compare amounts or quantities using proper and improper fractions and mixed numbers. So all this means that we're gonna order and compare fractions and mixed numbers first, and then we'll add and subtract. But what are proper fractions? Proper fractions are the ones like this, where the top number is smaller than the bottom number, suggesting that this is less than a whole. The same thing over here. The top number 5 is smaller than 6, so that suggests that this is less than a whole. So this is called a proper fraction. And 5/4 though is an improper fraction, because 5 is greater than the 4, suggesting that we're going to have more than a whole. And these two are called mixed numbers because they are a mixture of whole numbers and fractions. So 3 1/2, 1 4/5. So let's try and order them. So we're going to put them in order from the smallest to the biggest. Now, just by looking at the numbers, and as I explained beforehand, there were some that were smaller than a whole and some that were bigger than a whole. So I know for sure that these two will be here at the front. Which one will come first, I don't know yet. Then we'll have the other 3 numbers. But I'm thinking I could sort these out and place them here as well, without doing any calculations yet. So we've got 3 1/2 and 1 4/5. So that immediately tells me that number in front, that whole number, tells me that this is bigger than this, because it has 3 whole ones already, whereas this is less than 2. And looking at this one, this is more than a whole. So, but it's not anywhere near having 3 whole ones, because then it would be 12/4, and 5 is not. 12 is much smaller than 12. So the biggest out of these would be 3 1/2. We agree with that. And there was this discussion between them too, which one is the biggest, so that we can put it here. If I try and represent 5/4, so that would be 4 quarters here and another quarter. And if I try and represent this, so there is a whole, I'll do it out of 5 because this is what the fraction is telling me. So a whole, so 5/5 and 4/5. So if you try and compare this with that, as you can see, most of this is highlighted. So this is definitely bigger than this one. So we're safe to say that 1 and 4/5 is greater than 5 quarters. But again, 5 quarters is actually bigger than those two because this is the only one that is greater than a whole. So I can place this as well here. Now it's a question of comparing these two. So 2/5 compared with 5/6. So I'm going to try and bring them to the same denominator, because that means having the same number of slices and the same size of slices, so then they can be comparable. So 5 to bring to a number that can be divided by 6 and give whole numbers as well. So in other words, that's finding a common multiple. So multiples of 5 would be 5, 10, 15, 20, 25, and so on. And multiples of 6 would be 6, 12, 18, and so on. So the one that could be in common for both is 30. And I can easily do that by multiplying 5 by 6. So 5 lots of 6 or 6 lots of 5 give me 30. So I multiplied 5 by 6 to give me 30. So I need to do the same to this number at the top to keep the fraction the same. So 2 times 6 will give me 12. And in order to bring the 6 to 30, we'll multiply by 5. So we'll do the same to the top number. 5 times 5 is 25. Now it's very clear which one is the bigger one, because they've got the same denominator. So this is 12 out of 30 and this is 25 out of 30. So 25 out of 30 is definitely bigger. So I'll place them in order here. So 12 out of 30, that was 2/5. And 25 out of 30, that was 5/6. So I've now placed them in order from the smallest to the largest. Now you're probably wondering if these improper fractions were not clearly the biggest ones, or if you had two mixed numbers that were very close to each other, how do we compare and order them? So that's what I'm going to show you now. So in order to bring the mixed numbers as close to a fraction, then we'd need to convert them to improper fractions, like these ones. So what I would do is convert these. So 3.5 means they have 3 lots of whole pizzas or whatever you're talking about. So I'll show this as, because it's halves, so I'll show this as 1, 2, 3, and I have there. So these are highlighted. So how many halves would I have in total? That would be 2, 4, 6, 7. 7 halves. And the shorter way to do it would be to look at how many parts that are in the whole, and that's 2, and multiplied by the number in front. So 3 times 2 is 6, and the 1 that we have already, so that is 7. So 7 halves. And trying to convert this other one as well, so we get 1 whole, so that is split into 5 equal parts, and 4/5. So that 5/5 already in there, because that's what 1 means, and we have 4/5 as well. So 5 and 4 makes 9. So 9/5. Now once we have them like this, so we've converted them to improper fractions, we can easily compare just like we did before. So we need to find common denominator between 5 and 2, and the easiest one to do would be 10, because 5 times 2 is 10. So to get 2 to 10 we multiply by 5, so I multiply by 5 the 7 as well, so that is 35. And let's convert this as well. So 5 times 2 gives me 10, so 9 times 2 gives me 18, and as you can see clearly 35 out of 10 is bigger than 18 out of 10. So that suggests that 7 halves is greater than 1 and 4/5. So now let's have a look at if we had 3 fractions to compare with each other, what would we do? So we compared those two, but what if we had these 3 to compare using calculations, because we did a comparison before using common sense. So again, so the first thing to do is to convert all of them into improper fractions. This is already an improper fraction, so we don't need to do anything yet, and this needs to turn into an improper fraction, and as we looked at before, we converted that to 9/5, and we converted this to 7 halves as well. So it's a case of comparing 7 halves, 9/5, and 5/4. Now finding a common denominator, that means a multiple of all of these. So I used 10 between them two, multiplied 2 by 5 to get 10, but 10 won't actually work with 4 because you can't really get a whole number if you divide 10 by 4. So we're going to look for another multiple. So you could either continue listing the multiples of 5 and 2 and 4, and I'll show what that means. So if I go 2, because that's the denominator, then 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and so on, or you could stop at any point. And the multiples of 5, so 5, 10, 15, 20, 25, 30, bringing it to the same point. And multiples of 4, so 4, 8, 12, 16, 20. I don't need to go any further because I can see that 20 is appearing in all 3 of them, and that is what I'm after. It's a number that we can multiply all of these by and give an answer of a whole number. In other words, finding a multiple, a common multiple of all of them 3. So 20 is the multiple we're going to be using. So we'll have 20, 20, 20. So let's convert this to a fraction with a denominator of 20. So to get 2 to 20, we'll multiply by 10. So we need to multiply 7 by 10 as well to make 70. To get 5 to 20, we'll multiply by 4. So we'll do the same. So 9 times 4 is 36. And to get 4 to 20, we'll multiply by 5. So we'll do the same. 5 times 5 is 25. Now, as you can see, the biggest one is this one, 70 out of 20. The next one is 36 out of 20. And the smallest one is 25 out of 20. So that is very easy to order them. So we've been able to order and compare them. What about adding and subtracting? Adding and subtracting is very similar to what we have just done when we ordered and compared. So if I want to subtract 5 quarters from 1 and 4/5, so 1 and 4/5, take away 5 quarters, I would just convert them like I did into improper fractions. So that was 9/5, and that was 5 quarters, and then bring them to have the same denominator. So 9/5 was 36 out of 20, and 5 quarters was 25 out of 20. So that is easy to take away now, because all you need to do is 36 take away 25, and that gives us 11 out of 20. So exactly the same. All you have to do now, rather than compare them, put a minus symbol in between them, between the two that you are subtracting, finding the difference of. And the same thing would be if I wanted to take away 1 and 4/5 from the 3.5, I would just do this. So 70 out of 20, take away 36 out of 20. How would we add? Again, 36 out of 20, add 25 out of 20. So that is 61 out of 20. That was the most important bit, or the hardest bit to do, because with these two it must have been even easier, because we converted them to make them with a denominator of 30, because 5 times 6 was 30. So what we had then was 5 times 6, 30, 2 times 6, 12, and we have with 30, so we're multiplying by 5, so that's 25. So adding them together, 12 and 25, 37 out of 30. If you want to subtract one from the other, if you want to subtract 2/5 from the 5, 6, then we'd have 25 out of 30, take away 12 out of 30. So that gives us 13 out of 30. 13 out of 30. I'll rewrite it there. Or if you want to subtract 5/6 from the 2/5, then 2/5 was the same as 12 out of 30, take away 25 out of 30. So if you do 12 take away 25, that gives us minus 13. So it's the same as doing 25 take away 12, 13 minus, so the negative. So minus 13 out of 30. So I hope I've shown you here how to order, add, subtract and compare proper and improper fractions and mixed numbers. Practice this with fractions that you might be given, make them up, use dominoes because they look like fractions, add them up, subtract, order, compare them, because you need this skill in everyday life when it comes to sales, when it comes to adding and subtracting different amounts. In this video, we'll learn to express one number as a fraction of another. Fractions come into play when it comes to sales, for example. So if the original price of coat was £48 and then it is £24 off, so what fraction of the price is off now? So if it's £24 that it's off out of the 48 that was originally or in total, then that is the raw fraction, that's the fraction of it. But we can simplify this further to find a more simple fraction. So 24 out of 48. Now, just by looking at that, I can see that 24 is half of 48, so I could say half. But some people prefer to go the long way, and if they can't really spot it immediately, they would perhaps go and divide this by 2, because both of them can be divided by 2 or can divide by 4. So if I divide this by 4, we're going to have a 6, and if I divide this by 4, we're going to have a 12. So now I can divide both of them by 3. I can divide them by 6 immediately, so either way it would be fine. So if I divide by 6, that's going to be 1, divide by 6 is going to give me 2, so it is half price. Other fractions could be, let's say, work out what is maybe 12 as a fraction of 72, for example. So what's the number we're talking about? Is 12 out of 72. So what can you divide by? Is there a number that you can divide this both by? And 6 is one of them. So I divide this by 6 gives me 2. And if I divide this by 6, it's going to give me 12. So again, I can still simplify this, and this would be divided by 2 to give me 1. And this would be divided by 2 again to give me 6, so 1/6. 12 is 1/6 of 72. So all you have to do when expressing one number as a fraction of another is write down what is that number that you're talking about, out of what total, of what original price, what original quantity is that, and then simplify it further to get to a simple fraction. In this video, we'll learn to order, approximate and compare decimals. So I've got 5 decimals here: 4.36, 4.368, 42.6, minus 0.72, 0.274. So I'll compare them. If I'm to compare these two, which one would be the biggest one? So this is 4.36, and if it was money, it would be £4.36. Whereas this would be £4.36 and also 0.8 of pennies. Now, we don't have a coin to represent that, but it means an extra amount, and you can see this in petrol stations or in the bank. So it is less than a penny, but it is extra, so it's more than we have in here. So in this case, having 3 digits after the decimal point, it means that the number is bigger, but that's not always the case. So sometimes you'd have a decimal with fewer digits, like 4.5, and 4.5 means 4.5, so that's bigger than this one. So between these two decimals, the first two, this is bigger, so this is smaller. Then we have 42.6, so that's bigger than these two, because we have 42 whole ones. If it was money, it'd be 42 pounds and then 60 pence. This is minus or negative 0.72, so this is much smaller than any of the positive numbers we have here, because if it has a negative, it means it's a smaller number, and we've looked at that in thermometers or number lines. And then we have 0.274, so that means 0 whole ones, so that's smaller than any of these three. So I'll start off with this one because this is the smallest, it's a negative, so minus 0.72, because we ordered them from the smallest to the biggest. And then the next biggest one would be this one, because it has 0 whole ones, whereas this one has 42, this is 4, and this is 4. So 0.274. And then that would come between them 3. We discussed these two were smaller than that, so this is going to be the next one, 4.36, and then 4.368, and finally 42.6. So we've ordered them from the smallest to the biggest. So always first look at the whole number. The bigger the whole number, the better. If it's a positive, that should come before a negative in terms of the biggest. And then we look at the decimals. We looked at the digits after the decimals. So the next digit after the decimal has a bigger value than the one on the right of it. So these start decreasing in value. So we look at the whole number first, and then the first digit after the decimal point, and then the second digit, and then third digit, and so on. Now we'll try and round or approximate a decimal. I've picked one of these, 4.368, to the nearest whole number, so that we get rid of the decimal. We have a whole number, no decimal point, no digits after it. So is it going to be a 4 or a 5? Because this is between 4 and 5. So it is 4.368. So we look at the one next to it on the right. That's a 3, which suggests we stay down, because we've said if it's 0, 1, 2, 3 or 4, then we round down. So this is gonna stay as 4. It won't go up to 5. If it was a 5, 6, 7, 8 or 9, then this would be rounded to 5. Now looking at rounding to the nearest tenth or 1 decimal place, because it means the same thing. So that's the 10th, because we need 10 of them to make a whole. And it's 1 decimal place because it's 1 digit after the decimal point. So we need to round up to this point, so get rid of the 6 and the 8, but the 6 impacts this. So it's a 6, so we're going to round up. So this is going to be 4.4. Now to the nearest hundredth, because we need 100 of these units in there, 100 of these coins, 100 of any one that might be here to make a whole. So that is 600ths in there, so we're going to have to round up to this point, so we get rid of the 8, so we have only 2 digits after the decimal point. So that impacted those, so this means that this is going to be rounded to 7, so 4.37. And the thousandth, to the nearest thousandth, it's this digit that represents it, so we need 1,000 of any 1 digit that is here to make a whole. So we round again to 3 decimal places. We haven't got a digit here to impact it, but we know that when there is no digit, it's a 0. So that means we're going to round down. So this is going to stay as 4.368 as it is. So this has shown you how to order, approximate and compare decimals up to 3 decimal places. In this video, we'll learn to add, subtract, multiply and divide decimals up to 3 decimal places. So we'll start with addition, we'll then subtract, multiply and divide. So adding up is pretty similar to adding in general, so adding whole numbers. You've got to line them up so that the value of the digits matches with the ones underneath. So that's the units matches with the units, tens matches with the tens, tenths match with the tenths, hundredths match with the hundredths, and thousands match with the thousands. So we haven't got a digit here, but we can fill it with a 0 if we want, because we've said that zeros after the decimal point don't make any difference. And a clue here is if you've lined up the decimal points, then pretty much everything else is fine. So do that and it's sorted. Then treat it as you treat whole numbers. So 0 and 3 is 3, 6 and 8 is 14, so 4 and 1 carried over. 3 and 1 is 4, because 0 doesn't add up anything. 4 and 4 is 8 and 1. So I transferred the decimal point as I went along, in line with the other decimal points. So 18.443 is the answer for this. Then looking at subtraction, again, no digit here, so we'll add a 0. Lined up, so we've got decimal points under the decimal points, units under the units, and so on. So 0 take away 2 gives us a negative, so we'll borrow 1 from this, so this becomes 1 and this becomes 10. 10 take away 2 gives us 8. 1 take away 4 gives us a negative, so we'll borrow 1 here, so this becomes 11. 11 take away 4, that will give us 7. And 3 take away 3 gives us 0. Transfer the decimal point. 7 take away 4 gives us 3. 1 take away 0 is 1. So the answer is 13.078. In multiplication, again, we treat it as whole numbers, ignoring the decimal points, and then we add the decimal points later on. So we'll treat this as 74,834 multiplied by 1,624. So we'll start with the 4 again. So 4 times 4 is 16, so 6 down and 1 carried over. 4 times 3 is 12 and the 1 is 13. So 1 carried over. 4 times 8 is 32 and the 1 is 33. So 3 carried over this time. 4 times 4 is 16 and 3 is 19. So 9 and 1 carried over. 4 times 7 is 28 and the 1 is 29. So we're finished with the 4, we move to the 2. So again, that if it was whole numbers, that would mean 20. So I'll put a 0 down and then treat it as 2. 2 times 4 is 8. 2 times 3 is 6. 2 times 8 is 16. So 6 and 1 carried over. 2 times 4 is 8 and the 1 is 9. 2 times 7 is 14. So finish with the 2, move to the 6. So we put now 2 zeros, because there are 2 digits after the 6. So we got 6 times 4 is 24, so 4 down and 2 carried over. 6 times 3 is 18 and the 2 is 20. 6 times 8 is 48 and the 2 is 50. 6 times 4 is 24 and the 5 is 29. 6 times 7 is 42 and the 2 is 44. So we're finished with the 6 as well. So we've got 1, 2, 3 places there now. So 1, 2, 3 and carry on with the 1. 1 times 4, 3, 8, 4, 7 because when you multiply by 1, the numbers don't change. We add these up, so we've got 6 here, we've got 11, so 1 carried over, 10, 13, 14, 10, 19, and the 1, 20, so it's 2. Now add these, there's mixed 20, 23, so 2 carried over, so 8 and 2 is 10, 19, 21, 25. So we've got 5, 9, 11. 7 and 4 is 11, and the 1 is 12. So we've got this number now, and what we're going to do now is place the decimal point. Where does it go? Now, the way we do this is we calculate how many decimal places there are in the first number, and there's 1, 2, 3. So that's the digits after the decimal point. So we've got 3 here, and we've got 1, 2, 3, 3 here as well. So 3 and 3 make 6. So I need to give this answer 6 decimal places. So I go 1, 2, 3, 4, 5, 6. So the decimal point needs to go here. So the answer is 121.530416. Now we'll look at division. So we're dividing 8.662 by 1.42. So in order to turn this into whole numbers so that we can easily work with them, we would write this as 8662, so point over 1.42, because that's how we've got them. I'm just writing them as a fraction. So I need to get rid of these. So if I multiply them both by 10, I would then have 86.62 over 14.2. If I multiply them both by 10 again to keep the fraction the same, I'd have 866.2 over 142. And then finally 8662 over 1420. So that is whole numbers now that we can work with. We can simplify, halve, and so on. I would have preferred to have stopped here and plug it in there, so the decimal point would go after this second 6, and it would have 142. So how many 142s fit into 866? And it is 6 of them. So 6 times 142, which we can do quickly, that is 852. So we've got 13 left. So, well, actually it was 852, so that means 14 left, not 13. So now we have 142, so that is one lot. But at this point, when you finish with this number where I crossed out, we put a decimal point here as well. So 866, we fit it 6 lots of 142, put a decimal point wherever that is, and then put in the next digit, which was 1. So that gave us 6.1. In this video, we'll learn to understand and calculate using ratio, direct proportion, and inverse proportion. What is ratio? Ratio shows exactly how much of each part, or how many of each part or ingredient are needed to make the total, to make a drink, to make a mixture. For example, you might need 1 part juice and 4 parts water to make a drink. So if I have 2 parts juice, how much water do I need in order to make the mixture? So what's happened to the 1 part of juice? it is that it has doubled. So that part of water, or the amount of water, will double as well. So that bit will become 8. And what do we notice? 1 part juice and 4 parts water makes 5 parts or 5 units of drink. So again, when we've doubled, what's happened to the total amount is that it's doubled as well. So when you double the ingredients, the total doubles as well. So by using the ratio 1 to 4, we worked out how much water we'd need if we used 2 parts juice. And also we looked at the total. So if we're using 1 part juice, that could be maybe 100 milliliters of juice mixed with 400 milliliters of water. And as you can see, this is 1 part, so the amount of water is 4 times the amount of juice. And that's what's happened here as well. Even when it doubled, the amount of water is 4 times the amount of juice, because 2 times 4 makes 8. So let's have a look at another question. If, let's say, Jake and Omar share money in this ratio, so 2 to 3. So if Jake gets £2, Omar will get £3. So how much money would Jake get if Omar got £30? So we'll look at what's happened. From 3 to get to 30, we multiplied by 10. So we've gone in 10 steps, doubling and then multiplying by 3, 4, 5 and so on till we got to 10. So we kind of skipping those steps and we're going straight to 30. So Omar's got 30. How much will Jake get? So as we said, the same thing happens to every ingredient. If this was multiplied by 2, this was multiplied by 2, and this was multiplied by 2 as well. Now this has been multiplied by 10, so it's growing in proportion. This is what we call direct proportion. And so the amount that Jake will get will be 10 times larger than what the ratio says. So 2 times 10 equals 20. So both of them were multiplied by 10. So through the ratio and direct proportion, we're able to find how much there is in one of these two. So to find the specific amount, if you know how much Omar got, then you can find how much Jake will get. Or if you found how much Jake got, then you'll find how much Omar, through that, how much Omar will get as well. So that's one question that you could answer by using ratio and direct proportion. So we'll now look at another type of question using ratio and direct proportion. So Anne and Hannah will share chocolate bars in the ratio of 5 to 4. So when Anne gets 5 bars, Hannah will get 4. So how much will each of them get if there are 54 chocolate bars in total? So where does that go? Does it go under Anne's amount, under Hannah's amount, or is it the total? That is actually the total. At the moment, if Anne gets 5 and Hannah gets 4 bars of chocolate, that is 9 in total. But that's due to change because we're saying there are 54 available. So that is 54. If you like, you can call this the totals column. So 9, to get to 54, we multiply by 6. So this is gone 6 times bigger. So what we've learned is that these must be multiplied by the same number as well. So 5 needs to be multiplied by 6 and 4 needs to be multiplied by 6 as well. So 5 times 6 is 30 and 4 times 6 is 24. Does that add up to the total? So 30 and 24 gives us 54 as well. So we've split it, or we've shared it correctly. So we've used the ratio and then we increase these in direct proportion in all of these 3 cases. What we'll look at now is inverse proportion. So we'll see what inverse proportion means. It takes one person 4 days to build or to actually paint a whole house. So one person takes 4 days. We'll now look at how long will it take 2 people to actually paint the house. Is it direct proportion? Do we expect the number of days to increase? We know that that's not the case, because if there are 2 people involved, it's not going to take as long to build or to paint the house. So what happens is something slightly different when it comes to inverse proportion, because this is inverse proportion. So this grows bigger, this grows smaller. So what's happened from 1 to get to 2? We multiplied by 2. Now, in direct proportion, we said we'd do the same, we'd draw the arrow and multiply it by 2. But we don't expect 2 people to take 8 days to paint the house. So we don't expect this to double. What's going to happen instead is the opposite. So this will be divided by 2. So 4 divided by 2 makes 2. So 2 people will take 2 days to paint the house. So in a hospital, when there is 1 nurse available, she's got to see all of the 12 patients in the ward. What's going to happen if there are 3 nurses available? So what's happened to the number of nurses? It's been multiplied by 3. So what's going to happen to the number of patients is that it's going to be divided by 3, because they will share the patients. They will look after fewer patients. So that's what they're going to do. So 12 divided by 3 gives us 4. That's how many patients each. So how many patients they will look after, each of them. So as you can see, this is what we call inverse proportion. So one amount, ingredient, one side increases, the other decreases. Whatever you multiply this side by, you divide the other side by. And when it comes to direct proportion, we multiply both sides by the same number. So this is direct proportion. In this video, we'll learn to follow the order of precedence of operators, including indices. What does that precedence of operators means? It means which one of these do you do first. So we've got addition and multiplication in one sentence, in one question. Which one do we do first? And if you need to recap these, you can go back to a level 1 video in the same topic. But what we said there was that we do multiplication and division first, and then addition and subtraction. So 3 lots of 5 is 15, add 4 is 19. Now here we've got the same numbers, well, we've got some brackets around this. So 4 add 3 is 7. So 5 lots of 7, which is the same as this one here, 5 lots of 4 plus 3. So we've got to look at what is within the brackets first. So 4 add 3 gives us 7. 5 lots of 7 is 35. And that's the same thing here. 4 add 3 squared. So we're going to add 4 to the 3 squared. So what is 3 squared? That is 9. Add 4 to it, gives us 13. 4 lots of 5, or 4 times 5, add 3 squared. So 4 lots of 5, and these are being added together with 3 squared. So 4 lots of 5 is 20. Add 3 squared, which is 9. So that makes 29 altogether. We haven't got any brackets because if we had brackets here, that means we'd do these first. 4 times 5 is 20, add 3 and then square it all together. But we don't have that. That's why we're squaring the 3 only, because that 2 is on top of 3 only. 4 times 1 plus 2 squared minus 5. So it's 4 lots of this which has been squared. This is 1 plus 2 to make 3, and that's all squared, so 3 squared is 9. So we've got now 4 times 9 minus 5. So which one would I do out of these two? We'll do multiplication first. So 4 lots of 9 is 36, minus 5 is 31. So that's how we order these operators or operations. And another way that you could do this is through these letters. It's an acronym, BIDMAS. So B stands for brackets, I stands for indices. So indices are the powers that we have here. It could be 3 to the power of 3, 4 to the power of 3, 10 to the power of 5. So that, the power at the top, that's the power at the top. Squared, cubed to the power of 4, to the power of 10. So what we call these, or another name for them, is indices. One is index, 2 or more indices. That's the plural form of it. It means powers. So we've said brackets first and then indices, and then division, then multiplication, addition, subtraction. So if we go back to these, what do we have to do? We've got addition and multiplication. So which one of them comes first? Multiplication comes first. So 3 times 5 I do first, and then I add. So that's what we did before as well. So 15 add 4 gives us 19. Now looking at this, we've got addition, multiplication and brackets as well. So which one of them comes first? BIDMAS, brackets comes first, so we do the brackets. So 4 add 3, which is 7, And then comes the multiplication because it's lower in the list, lower down in the list. So 7 times 5 gives us 35. And here as well, brackets first, 4 plus 3, which gives 7, and then multiplied by 5. Although we don't have a sign, but because it's in front of the brackets, it means 5 lots of 5 multiplied by 4 plus 3. And then here we've got addition, and we've got a power index. So index must come first. So I must do 3 squared first, which gives me 9. Add then 4 to give us 13. And here we've got multiplication, addition, and indices. So look at them. That's indices, that's multiplication, that's addition. So indices comes first. So we've got 9, and then we do multiplication. So we've got 20 plus 9, or 20 at 9, which gives us 29. And in this one, we've got multiplication, addition, squaring, which is in an index. So we're talking about indices, and subtracting. So look at them. Brackets come first because we've got brackets as well. So brackets, within the brackets, 1 at 2, that gives us 3. And then indices, so that means we're squaring it. 3 squared, which gives us 9. So then in between them two, we've got to pick multiplication because that comes first. So we go 4 lots of 9, and then we take away 5. And that's what we did here as well. That gave us 31. So this, I hope, has helped you learn how to follow the order of precedence of operators, including indices. In this video, we'll learn to calculate amounts of money, meaning we'll learn to add, subtract, multiply and divide amounts of money, and through this we'll learn to budget. So I've got the cost of 3 different items that I want to buy. One costs £14.75, the other £142.50, and finally £4,253.46. I want to find out what is the total cost of all of these. So I've lined them up, making sure I've got the decimal points under each other, so that I'm adding pennies under the pennies, and I'm adding pounds with the pounds, and so on and so forth, not mixing them up, because that would give me a different answer. So there we have 11, and then 17, and then 10, 11, 4, so £4,410.71. To double check that I've got this right, I'll round this up. So I've got 15, 140, 4,003, 4,300. So 5, 5. So this comes close to this one. That shows that I've got the calculation right. So I've got a budget of £5,000 for these items, and I want to find out how far off I am from that limit, from that budget. Do I have much money left? So that's what I'm going to work out now. 5,000, take away £4,410.71. So I haven't got any pennies for the £5,000, so I'll add these 2 zeros because they make no difference. So I'm going to try and take away 1 from the 0, but it's going to give me a negative number, so I'm going to try and borrow from these. So I can't really do through these ones, but I can do it with the 5. So 5 will become a 4, and this becomes a 10. Now this one can borrow from this to make it a 10, and this becomes a 9. This becomes a 9, and this is a 10, 9, 10, 9, 10. So 10 take away 1 is 9, then we have 2, then we have 9, 8, 5, and that's it. So this is £589.29 left. Again, if I round this down to 4,400, I'll need about £600 to get to 5,000, and this is roughly £600. Now I want to find out whether I can purchase some more items. So I want to get 16 towels, which cost £13.50 each. So we'll go 6 times 0 is 0, 6 times 5 is 30, 6 times 3 is 18, and the 3 is 21, 6 times 1 is 6, and the 2 is 8. So I'm ignoring the decimal point for the time being, and then we'll put 0 down. So 1 times 0 is 0, 5, 3, 1. So we've got 11. Now we've come to this point where we've got the answer, but we need to do a final thing. So we'll count the decimal places for the two numbers. There is a decimal point, so we've got 2 digits after the decimal point. So there are 2 in there, and we haven't got any here because there is no decimal point at all. But if it was, it would be here. So no digits after it. So we'll give this final answer 2 decimal places as well. So we go 1, 2. So the answer will be £216. I can see that I still have some money left, so I'm gonna work out how much I've got left and then buy some books with the remainder. So we've got £589.29. Take away £216. So 9, 2, 3, 7, 3. So I've got £373.29 left, and one book costs £15. So I will find out how many I can get because I want to use all this money on books. Okay, so 373.29 divided by 15, because that's the cost of each book. So we go, how many 15s fit into 37? That's going to be 2 of them, because that makes 30. So we've got 7 left then. So how many 15s would fit into 73? And that's going to be 4, which makes 60. So we've got 13 left. Now at this point we've got a decimal point, so we've got to transfer it over here as well. So now we need to find out how many 15s would fit into 132, and that's going to be 8 of them. So we've got 12 left, and that's again 8. But if we come to this point and we've got a decimal point, that means we really can't get 25. It's only 24, because you can't buy parts of books. So we'll be able to buy 24 books, and we can work out how much there will be left. So 24 times 15, which is the cost of each book. So we go 20, 12. So we put a 0 down, 4, 2, 0, 6, 3. So 360 was the cost of this, and from the £373.29 that we have left, take away 360. That's 9, 2, 3. So it's £13.29 left after all the expenses. So what we've learned through this is that it is important to know what is your budget. And as we said, if we want to work out the total cost, we add things up. If we want to work out how far off we are from the budget, then we subtract the total cost from the amount that we have available. If we want to buy multiple items, then we multiply the cost to work out what is the total cost. If we want to work out how many of an item we can buy, like the books that were £15 each, then we need to divide from the amount that we have left, divide that by the cost, and that will give us the number of the items that we can buy, like the 24 books that we can buy here. In this video, we'll learn to calculate amounts of compound interest. What is compound interest and how is it different from simple interest? For that reason, I'll contrast simple and compound interest so that you can learn how to work out amounts of compound interest. So I've shown simple interest in blue and compound interest in red. We do use, or we get interest when we invest amounts of money. So we're going to assume that we invest in £100 in both cases for the simple and the compound interest. So in year one, at the end of year one, if the percentage of interest that you get is going to be 10, so 10% interest in both cases for both in simple and compound interest. At the end of year one, if you've invested £100, you're going to end up with 110 because £10 is 10% of 100, and that is the interest rate. And the same thing over here, if you receive compound interest, you're going to get £10 extra, so you're going to end up with £110. And we'll show that using a simple method, which is called the multiplier method. So if I multiply 100 by 1, I'll get just 100. If I multiply 100 by 1.1, which is what this represents, then that means we'll get 110%. So I'll go 100, which is the amount that we're investing, times 1.1, which is the whole part, which is £100, and 0.1 represents the extra 10%. So it is, in other words, 110%. So that gives us £110. And the same thing on the other side, that's how we work it out. So we've got 100, which is the principal amount or the initial amount, times 1.1, which is 110% converted to decimal, is equal to £110. Now in year two, what happens in year two? In year two, if you paid simple interest, you're going to get the £100 and the £10 and the £10 because you get 10% no matter what. So you get, at the end of the first year, you got 10%, which was £10. And at the end of year two, you're going to get an extra £10. So the amount of interest doesn't change. So just by looking at it, you'll know you're going to get £120. But to work it out, we get the initial amount, which was what we invested, times 1.2, because it's 110% in total now. That gives us £120. So up to this point, that's what you had at the end of year one. This is the extra amount that you're getting at the end of year two. And looking at compound interest, what you get in the second year is actually 10% of this whole amount, not 10% of the £100 they invested, but 10% of whatever you accrued at the end of year one. And then in year three, you're going to get 10% of what you had at the end of year two. So you get 10% of this whole amount, not just the £100 that you invested. So that's the difference between simple and compound interest. So again, to work it out, we got £100 that we invested, and then we multiplied it by 1.1, which means 10% extra, to get that first year figure. But now for the second year, you're going to multiply this by 1.1 as well, because you're looking at find that increase of 10% for the amount that you had in total at the end of year 1. So again, we worked it out here. That was the 10% of the 100. Whatever we invested, that's the 10% that you get all the time. Whereas here you get now an extra 10% of this whole amount. So for that reason, we multiplied by 1.1 and by 1.1 again. So that gives us in total £121. You see, that's more than the simple interest one. If you want me to explain this in a more simple way as well, we had 100, we got 10%, so that was £110 at the end of the first year. The next year, you've got now 110, so you're going to get 10% of this amount, not the 100, the 110. So 10% of 110 is 11, because we just knock off a 0. So that's what we had. We had 110, added the 11 on top, that makes 121. Now looking at the third year, going to simple interest, we would just add the £10 on top. So going to be 110 and 10 and 10, 130. So £130, which could be the same as saying just adding 30% on top the 100 that we got, because it's 3 years, 10 and 10 and 10. So that is 100 times 1.3, that gives us £130. Whereas over here, you probably expect more now. So we've got the 121, and that's 121. Now we'll add 10% of this 121. So the way to work it out will be, well, just repeat this first, whatever we had. So 100 times 1.1 times 1.1, that gave us 121. We'll multiply that now by 1.1 again, because it's the third year. And what does that give us? We can work it out in our head as well, because 121, 10% of 121 is 12.1, so £12 10 pence. So we had 121, add the 12.1, gives us 133.1, which in pounds will be £133 and 10 pence. So again, comparing it with simple interest, we've got more money with compound interest. So what do you notice here? How did we work it out? So we had 100 first, which was the initial amount, so always comes the initial amount. So 100 times by, where did we get that 1.1? Why is that 1.1? So that's the decimal form of 110%. So 100, because if you multiply it just by 10%, it's going to give you only the small amount. We want the 100 and the 10% on top. That's why we say 1.1 rather than 0.1. So times 1.1, because 10% was the interest rate. So if the interest rate was 2%, we would have 1.02. And how many times was this repeated? It was 1, 2, 3, because it was 3 years. So, and we know that the short form of doing this will be with a 3 at the top, to the power of 3. So that, if I just input that into the calculator, that should give me the same answer. So we'll do that together. So we go 100 times 1.1 to the power of 3. So that gives us 133.1, which is the same as £133 and 10 pence. So we'll do another example. So we've got £1,500 which will be invested. Let's look at one example. So we've got £1,500 to invest, and it will be of 5 years at 3% compound interest rate. So we'll do 1,500, which is the initial amount, multiplied by 1.03. So it's adding 3 pennies on top of the pound, and then that will be with a 5 at the top, which means to the power of 5, because this would be repeated 5 times. So we get a calculator to work it out. So 1,500 multiplied by 1.03 to the power of 5, which gives us £1,738.91. Now, if you didn't have a scientific calculator, you could have just done 1,500 times 1.03 times 1.03 times 1.03 times 1.03 times 1.03, so 5 times, because it's 5 years, and that gives us exactly the same amount. Just be careful to not put 0.03, because that's gonna dramatically reduce the initial amount rather than increase it, which means that it's going to give you only the 3% rather than the 3% on top of the 100. And let's look at a final example. Let's say we're investing £15,272 over 2 years. So at the end of year 1 you'd get 5%, and at the end of year 2 you'd get 4.5% compound interest. So what do we multiply? So we start as always with the initial amount, which is 15,272, multiply that by 1.05, because that's 5% on top of the initial amount, and then multiply that by 1.045. So that is 4.5%. So 4% would be 1.04, just like 4 pennies on top of a pound, and then a half of it comes after the 4. So that is 1.045. Plug that into the calculator. 5272 times 1.05 times 1.045, and that gives us a total of £16,757.20. In this video we'll learn to calculate percentage increase and decrease, discounts and tax. Percentage increase and tax work pretty much in the same way, because you add on amounts, you increase in the amount that you've got to pay. When it comes to tax, so it could be a certain percentage, which is the same as a percentage increase. And percentage decrease and discounts work pretty much in the same way as well. So we'll have a look. So we've got an amount which is 100%. So let's say we've got £220 is the original cost of a coat, and there will be an increase in price by 17%. So what is that amount? So the way to work it out is really work out 17% of 220, because this 17% is the same as any 17% within the whole amount. So 17% of 220, there are different ways you can work it out. The easiest and the most straightforward one would be to get the total increase. So we go 100% and 17, that is 117%. And we can write that as a decimal 1.17. And then just multiply it by the amount, 220, the 100% amount, and that will give us the price with the increase included. So 1.17 times 220, that is 257.40 £. But there are different ways you could have worked this out, such as doing 17% first. So 17 divided by 100, or out of 100, times 220, which is the original amount, and that gives us just the 17%. Or if you want to do it all together, same thing. So 117% all together divided by 100, which gives us 1.17 times 220. So these are just some of the ways, and you can use any method that you like. So that's the increase. Now let's say we've got the price of one item is £123. Now you've got to pay 23% tax on it, so that's going to be on top of that price that you're paying already. So that could be VAT, for example. So we're gonna add that 23 on top of 100, so that is 123%, and as a decimal that is 1.23 multiplied by the original amount, or the 100% amount, which is £123. So that is 1.23 times 123. So that gives £151.29. So that is the new price, or the price with the tax included. What we could have done as well is, okay, let's get 23% of 123 and then add it on top. So 23%, 23 out of 100 times 123, and then that amount can be added on top of 123, which was the 100%. Either way, it will give you the same answer. So as you can see, increase and tax, you're talking about something being added on top of the 100%, on top of the original amount. Now let's look at decrease and discounts. So we've had an item costing £400. Now there's been a decrease in price. This price, this was the 100%. Now it's been reduced by 19%. How do we know that? Because 81 and 19 makes 100. So what I can do is I can work out 19% of 400 and take it away. Or I can just work out what is 81% of the 400. So 81% as a decimal, 0.81 multiplied by 400, and that should give me this amount. So 0.81 times 400 is equal to £324. So that is the reduced price. And same thing with discounts. So discount means a reduction in price. And again, if we had an original price being £215, so all of this being 215, there's been a reduction or a discount by 55%. So I can work out 55% of this and take it away from 215, or I can just work out 45% and that's it. It's worked out. So I'll choose the easy version. So 0.45, which is 45% written as a decimal, multiplied by 215, which is the 100% amount, and that gives me £96.75. So this method that I use is called the multiply method. Is a straightforward one if you use, or if you can use, a calculator. And to recap, we said increase and tax work pretty much in the same way, and decrease and discount again work pretty much in the same ways. When it's increase, you add in an amount on top. You're sometimes given the amount, sometimes you're given the percentage, so you've got to work out the amount. And when it comes to the decrease, the price or the amount will go down, and we're given one of the percentages, we're given either this discounted percentage, or we're given that final amount or percentage, and we've got to work with that to get the answer. In this video we'll learn to convert between metric and imperial units of length, weight and capacity using a conversion factor and a conversion graph. So we've got 1 kilometer is approximately 0.62 miles. This is what we call a conversion factor. So we use this to convert kilometers to miles or miles to kilometers. So let's suppose I want to work out how many miles there will be in 4 kilometers. So to get from 1 to 4, we've multiplied by 4. So we'll need to do the same on the other side, because these actually grow in proportion, in direct proportion. If you increase, or if you double the number of kilometers, you need to double the number of miles as well that you have there. So, or in other words, you're going to need to double 0.62, that conversion factor. So we'll go 0.62 times 4, that gives us 2.48 miles. So let's suppose I didn't have this, but I have this conversion graph instead. So we'll go to, there we have kilometers and miles. I'll go to 4 kilometers. So that is 4 kilometers at this point here. How many miles is that equal to? So if you use a ruler to draw a straight line forming a right angle, we'll see that this is about 2.5, 2.5. It's right in between 2 and 3. So that's what this gave us as well, the working out. Now we'll try another example. So we've got 1 kilometer is approximately 0.62 miles again. This is the short form of miles. So if we have, let's say we have 6 miles, how many kilometers will that be approximately equal to? So we'll need to find out first how many 0.62s fit into 6. So the way to do it is by dividing 6 by 0.62. So 6 divided by 0.62 gives us about 9.7. So I will need now to multiply 1 by 9.7, which is easy to do because it's 9.7 itself. So 6 miles will be approximately 9.7 kilometers. So let's have a look. We're looking at 6 miles, so we'll go straight to this point and we'll draw a straight line, a perpendicular line, which means forming a right angle here. So as you can see, is just a bit more than 9.5. So through the working out, we found out that this was 9.7 approximately. So in one go, I've actually used both the conversion factor and the conversion graph. So this is how you use both of them. This was the example for length. We'll now look at weight and capacity. So the example for weight that we've got here is pounds to kilograms, or kilograms to pounds. So we'll try one out with let's say we've got 6.5 pounds and what will that be approximately equal to in terms of kilograms? So to get from 1 to 6.5, we multiplied by 6.5, so we'll do the same on the other side. So we'll go then 0.45 times 6.5, which gives us 2.925 kilograms, which is roughly about 3 kilograms. So what we'll do that we'll plot it over here. So if we have let's say pounds here and kilograms on the other side, so I'm actually constructing a conversion graph myself. So I've put the two axes, and one is kilograms, the other is pounds. I've numbered them, equal spaces between each of them. So now we'll try and plot these points. So I'll plot 2 points so that I'm able to draw a line. So we've got as I said, 6.5 pounds. There is 6.5 is here in the middle. That is equal to about 3 kilograms. So that's going to be around here. So 6.5 and that's 3 kilograms about. So that's 1 point. And we also have a point here as well, because 1 pound is equal to about half of a kilogram. So there is 1 pound, about half of a kilogram. So I've got 2 points, and this helps me now draw the line, because I can connect these 2 points. And so I've made a conversion graph through this. And as we looked at in the example before, when it came to length, I can actually pick any of the number of pounds or kilograms and convert. So if I want to work out 12 pounds, what's that equal to in terms of kilograms? There we go. Draw the straight line, a perpendicular line up here, then another one, and you can work out how many kilograms that is equal to. So now we've moved to capacity, and we're converting between gallons and kilograms. So let's assume I want to work out how many gallons will be 10 kilograms worth. So 10 kilograms. So to get from 1 to 10, I've multiplied by 10. So we'll do the same over here, times 10, and that gives us 2.2 gallons. We're talking about imperial gallons here. So that is going to help me construct this conversion graph. So I've started again with these two axes. We've got gallons on one side and kilograms on the other. They could be swapped either way, and that would be fine. So we've got 10 kilograms, we go to 10 kilograms, that's kilograms, and that will match 2.2 gallons, so just over 2. So that's the point there. And we've also got here to tell us that 1 kilogram is 0.22 gallons, so that like 1/5, about 1/5 of a whole gallon. So we've got 2 points, and through these 2 points we can create a graph. So now we can use this to convert between kilograms and gallons, just like we did when it came to weight or capacity or length. So if I want to work out what are 2 gallons equal to, so I can draw a straight line, put a dot, and then another perpendicular line over there to get the number of kilograms. So I hope this has shown you how to convert between metric and imperial units of length, weight and capacity using a conversion factor and a conversion graph. In this video we'll learn to calculate using compound measures including speed, density and rates of pay. We'll start with the rates of pay because that you're more likely to have come across it before or to have used it in everyday life. So we've got the rates of pay, which are equal to pay over time. And how can we remember that? When you ask somebody how much they earn, they might say £10 per hour, £500 per week, or £2,000 per month, just a few examples. So what they're giving us is the amount or pay, however you like to denote that, with a P or with an A, however you find it easier to remember. So that would be the pay over time, because we're saying per hour, per week or per month. So to illustrate with an example, if somebody earns £1,530, for example, for 15 hours, then the way that we'd work it out, it'd be by dividing 1,530 by 15, and that gives us 102. So that is £102 per hour, because we input hours, so we said 15 hours, and that's what we get out. We input pounds, and that's what we get out as well. When it comes to speed, the working out is very similar to the rates of pay. So again, when you ask somebody what speed they're traveling at, or when you look at speed limits, you get something like 30 miles per hour. That means that within an hour they're going to travel 30 miles if they travel at a constant speed. So speed is worked out by dividing the distance, which is in this case 30 miles, it could be 50 kilometers, over time. So we've got that time here given in hours, but it could be in minutes, in seconds. So to illustrate with an example, we might have a car traveling at 45 miles for maybe 1.5 hours. So that's what we do. 45 divided by 1.5 gives us 30. So what is that 30? 30 is miles per hour. So whatever we import, that's what we get out. So for rates of pay and speed, it was quite straightforward because we can use the units that we describe amounts that we paid in everyday life or speed, and use those to get the formula up. So rates of pay equals the pay or amount over time, and speed is distance over time, and plug the values in and we get the answers. But when it comes to density, density is not as much of a familiar term, or the formula at least is not. So what I'm going to do very briefly, I'll show you two boxes of the same size. If one of these is filled with sheets of paper and the other is filled with tissues, then filled up, this is likely to weigh more. So the mass of this box will be greater. Now, when it comes to density, as we said, we look at mass as well as volume. So these two boxes have the same volume because they take up the same amount of space, but this one has a greater mass. As a result, this one is going to have a greater density because it has a greater mass. So for the same volume, one of them has a greater mass. So the way we work out density is by getting the mass and dividing it by the volume. Here is one example, 30 grams per cubic meter. So if the mass of an item is, let's say, 432 grams and the volume is perhaps 100 cubic centimeters. Now, what is its density? Again, 432 divided by 100, that gives us 4.32 grams per cubic centimeter. This last formula is more likely to be forgotten or to not be remembered. So here is a clue or a trick. So if I write m as a small m over v, these two together, they make the shape of a heart if joined together. So that's a way to remember it, perhaps. One last thing that I want to discuss here is that sometimes, although you might know the formula, it might be a bit trickier to work out one of the answers. The reason being is that sometimes instead of being asked to work out the speed, you may be asked to work out the distance or time. So let's illustrate. For example, let's say you've been given that the speed that the car is traveling at is 30 miles per hour. So that is 30 miles per hour. And you're also given that it takes the time that it takes the car to travel being maybe 1.5 hours. So that is the speed, and that's how long the car has traveled for. Now, can you work out the distance? And we know from this example what it is, but what if you didn't know? So if this value is missing, the actual distance is missing, how do you work it out? And I have a suggestion. I would like, if you don't know already what to do, I would suggest that you write a similar sentence to this one that is equal or that is true in maths. Let's say I can say that 3 is equal to 6 divided by 2. So it's very similar to this, but it is true at the same time. So actually 3 is equal to 6 divided by 2. So if I wanted to work out what is this figure at the top, just like the 6 over there, so how can I rearrange this to make it equal to that 6, so that I can say something like 6 is equal to what? So what do I do to 2 and 3? And I multiply 2 times 3. So I'm going to do the same thing over here. I go distance is equal to 1.5 times 30, which is equal to 45. And you can actually do the same thing, use the same method for any of these 3. In this video, we'll learn to calculate perimeters and areas of triangles. So what does perimeter mean? Perimeter is the rim. So going around the shape and adding all these sides. So 53, 60, and 80. That equals 193 millimeters. Now we've got this other triangle. So we have 5 and 5 and 5, which is 15 centimeters. So we had the same units, centimeters, but if we had different units, let's say a mixture of centimeters and millimeters, we need to convert those units first before we do any calculation. So we've got now 8 and 3.2 and 5.5. So that gives us 16.7. The unit is meters. Finally, we have this triangle here. So we follow the same procedure. We have 3.8, add 3.8, add 5.5. That equals 13.1 centimeters. So working out the perimeter is quite straightforward. It's going around the shape, adding all of the dimensions or the lengths or the sides. Now we'll look at area. Now rather than giving you the formula for the area of the triangle, we will derive it together. So I'm going to use some post-its to help me with this. So I have a rectangle, which you know the formula for its area, which is length times width. And this rectangle I'm holding has the same length and width as the triangle. So I'm gonna fold it in half. And you will see that this is equal to this. I'm gonna cut it now. I'm not being very precise, this is just to demonstrate. And you'll see that we have 2 identical triangles. So the area of the triangle is half the area of the rectangle with the same length and width. I could just multiply the 60 by 53 and then divide it into 2 parts. So this means that I could multiply 60 by 53 and then divide it by 2 to get the area of the triangle. So 53 times 60, that is equal to 3,180. . . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . 3 . and we'll divide that by 2. Which gives us 1590 millimeters squared. The same thing is applied with the other triangles, so I'm going to very quickly demonstrate again. And we have this rectangle which has the same length and the same height, so we'll cut it quickly so that we can see that that would make 2 triangles. So this would be the same as this, and the other triangle is made using these 2 parts. So putting this on top, it shows that they are of equal size. So the same thing again, you'd have to get the length, which is equal to 5, times the height. So this is really important. This is not the height, this is not the height, it's this one here, which is perpendicular to the base, or what I call the length, because it is related to the rectangle. So you, at this level, you're not required to work it out using any other formula. All you have to do is measure it. So by measuring it, you'd get 4.3, so 5 times 4.3, and then divide that by 2 to give us 10.75 centimeters squared. Following on with the next triangle, so you've got this as the base, although it's upside down, it does not matter, and we can draw a perpendicular line with the base to make the height. So we measure it using a ruler, and this is approximately 1.7 meters. That would be, this was centimeters, so I will go 8 times 1.7 divided by 2. That gives us 6.8 meters squared. Now, of course, this is not actual meters, so the drawing is not to scale. Same thing with the other one. We've got the base, we've got to get the height. So there'd be a right angle here, and this is approximately 2.7 centimeters. So I go 5.5 times 2.7 divided by 2 to give us 7.425 centimeters squared. Same thing as with the perimeters, you need to make sure you have the same units before you proceed with the calculations. And the thing to remember is that we always have squared, so the unit squared when you work out the area. So it's like finding how many little squares would fit in there of 1 millimeter long and 1 millimeter wide, or how many of those squares which are 1 centimeter long and 1 centimeter wide would fit into the area. In this video, we'll calculate perimeters and areas of circles. So we worked out the perimeters and areas of other shapes such as squares and rectangles, and we looked at dimensions that they have. So we're going to do the same now for circles. First of all, perimeter in the case of a circle is called circumference. So circle, circumference, it might help you make the link. And area is the same, so it covers all of it. We looked at length and width before. Now, in this particular case, we haven't got length and width, but we've got diameter. So, as you can see, diameter is drawn here from one side to the other, going through the center, and a radius is only half of it, so from the center to one of the sides. So you can see there are many radiuses. If you just draw them all out, there'd be many possible to show, but it's actually the same length. So there is basically one size for the radius. Same thing for the diameter. So radius is half the diameter, diameter is double the radius. What we're gonna see is how to get the formula for the circumference and the area. And there is a symbol that we use in both cases, and we'll see what that means. This is pi, so it's this symbol and it's called pi, not apple pie, although it sounds like that. So we'll see what pi means now, and I will get a piece of string and I'll cut the piece that is the same length as the diameter of this circle to demonstrate. Now, this is not something you're going to be required to do in an exam, but it's useful to help you remember the formula. So I've cut a string which is as long as the diameter, and I'm going to see how many of these will fit along the circumference. So starting here, roughly. So we'll make a mark at this point, and we'll start from that point again. So 2 of them already, and we can fit one more because there is some more space left that is not covered. So about 3, not exactly 3, but about 3. To be a bit more precise, this is 3.142, and even that is rounded because the digits continue forever. So all you need really is to remember it up to this point. You can see now why that is 3.142, because it actually means how many lots of the diameter fit into the circumference. And we'll use that pi for the area as well. But first of all, since you saw that it was circumference worked out as so we'll use this symbol for the area as well. But first of all, let's write the formula for the circumference. You saw that circumference was equal to about 3 lots of the diameter. But rather than writing this long number, which in fact would be even longer, we're going to write pi. So circumference is equal to pi lots of the diameter. Pi lots of the diameter, which you can also write as 3.142 lots of the diameter. So let's use an example. If I measured this and the diameter is equal to 5 centimeters, then to work out the circumference, we'll do 3.142 multiplied by 5, which is equal to 15.71 centimeters. About 3 lots of 5. Now we have this, which is 7 centimeters, so the radius is 7 centimeters, we are going to work out the circumference. So again, 3.142 times, we must be careful to not do it times 7, but times 14. So 43.988 centimeters. You may have seen another variation of the circumference formula, which is pi lots of the diameter. But diameter, we said, is the same as 2 lots of the radius. So we could write it as 2r in here. And the order can differ, so you could have the 2 in front, 2 pi r. So it should give us, in fact, the same answer. So if I just redo this, that's going to be 2 lots of 7 times 3.142, which is again equal to 43.988 centimeters. Now we'll look at the area of a circle. The formula for the area of the circle is equal to pi lots of r squared, the radius squared. So if we think of radius in here, radius squared would be this area, this square. Okay, so that's what this is. And this is telling me it's pi lots of them, so over 3 lots of them. So there is 1, 2, 3, 4. And as you can see, there is this space in here which is not covered. That's why it's not exactly 4. So it's 3.142 lots of radius squared. So in this particular case, the area is 3.142 times 5 was the diameter, so the radius is 2.5, and we'll have to square that, which is equal to 19.6375. That was in centimeters, so we're going to have centimeters squared because we're talking about area. And that's an indicator as well. That reminds you need to have squared at the end. Now we'll use the formula to work out the area of this circle. So area, again, pi r squared. And we know that pi is 3.142 multiplied by the radius. And radius was 7 centimeters here because this is the same circle, so we'll multiply it by 7 squared. 3.142 times the 49, so that is equal to 168.658 centimeters squared, again because we input centimeters. This was equal to 7 centimeters. If it was meters, then we'd put meters squared. Kilometers squared. So to summarize, there are same symbols used for both perimeter, which in this case is circumference of a circle, and area. So if we just look at this one, so circumference, 2 lots of pi r, and we'll write area as pi r squared. There is a 2 there and there is a 2 here. There is a pi and a pi. There is an r and an r. I prefer this much better. So when it comes to circumference, that 2 is in front. When it comes to area, that 2 is at the top. And you know that area is worked out in units squared. So that helps you remember it. So all you have to remember for this is 2 pi r for the circumference and pi r squared for the area. Same symbols, but the order of the two changes. So you put it in front for the circumference and at the end at the top for the area. You also have seen what pi means, so that should help you remember it. In this video we learn to calculate the perimeters of compound shapes. So perimeter is about going around, it's about the rim. So we're looking at fencing and things that would go around, like ribbon around a cake. So this means that I'll need to go around the shape and add all the measurements together. So I like to cross them out as I go along. So we've got the first one as 5 centimeters, and then 5 centimeters, another 5, there is another 5 and another 5. So all together this is 25 centimeters. Notice how I didn't count this because this is not in the outside. Now we've got another shape which is made of a rectangle in the middle and 2 semicircles. The 2 semicircles, if you put them together, they will make a full circle. So I can calculate the circumference of the full circle with a diameter of 4 centimeters and add it on top of these 2 lengths, which are 7 and 7 each. So we'll start off with the semicircle, which the 2 of them make in fact a full circle. So we'll do pi times the diameter, which is 4 times 3.142. You could do 3.14 as well. And what this equals to is 12.568. So we've got the circumference. Now on top of this we're going to add the 7 and the 7, which makes 14. So I've made sure I've calculated everything. I've added everything to this. So 14 and the 12.568 makes 26.568 centimeters. So we've got the third shape, which is made of a semicircle and a triangle. We'll first work out the perimeter of the semicircle, which we're going to work out by getting the circumference of the full circle and then cutting it in half. So the circumference of the full circle we find by multiplying pi with the diameter. So that is 3.142 times the diameter, which is 10. So that gives us 31.42. Now we'll cut this in half. So that is going to give us just this part. 31.42 divided by 2 is equal to 15.71. So we've got this part. Now we'll add 9 and 9. So this gives us 33.71 centimeters. The final shape is just a semicircle. So we can work out again the circumference of the full circle and then cut it in half. So pi times the diameter, that is 3.142 times 12, and that gives us 37.70 37.704. Now we'll cut it in half, so 37.704 divided by 2, that gives us 18.852. So we've worked out so far the perimeter of the semicircle, but to get the perimeter of the shape, we're going to need to add this part as well, because in this way then we can go back to where we started. We include in every part in the outside of the shape. So we'll go 18.852, add 12 to it, so that's going to give us 30.852 meters. So we'll now look at the area of this shape. So working out the area, and we'll start off with the first one. So we'll add together the area of the square and the area of the triangle. So the area of the triangle is worked out by base times height divided by 2, or length times width divided by 2, however you want to call it. So I'll go 5 times 3.5 divided by 2. So 5 times 3.5 divided by 2 gives us 8.75. I will add to that the area of the square, which is 5 times 5 equals 25. So 8.75 plus 25 will give us 33.75 meters squared. Now the next shape is made of a rectangle, which we can work the area of by multiplying 4 times 7, and then the circle. So we've got 2 half circles together which make a full circle, so we'll get the area of the circle first. So we've said the area of the circle is found by multiplying r with r squared. So 3.142 times the radius is 2 squared, which is 4. So 3.142 times 4 gives us 12.568. So 12.568 will add to that 4 times 7, which is 28. So 28 and 12 gives us 40. So this is 40.568 centimeters squared. That's the area of the whole shape. Now looking at the other one, it's made of half a circle and a triangle. So the area of the circle, again, we said we find by multiplying pi r squared. So 3.142 times r squared. R is 5, half diameter. 5 squared is 25. So we go 3.142 times 25, which is 78.55, but this is not a full circle, so I'm going to have to halve that now. So divided by 2, that gives us, so 78.55 divided by 2 equals 39.275. That is 39.275. So this is this area. Now we've got to calculate the area of the triangle, which you said is base times height divided by 2. So base is 10, height is 6. So 10 times 6 divided by 2, that is 60 divided by 2, that gives us 30. So we'll add 39.275 plus the 30 that we have for the triangle. That makes now 69.275 centimeters squared. So if we have different units, we'd have to convert them first before calculating. So we didn't have that in this case. All of them were centimeters, so the output was in centimeters as well. Now looking at the final shape, we've got half a circle, so we'll need to work out the area, and when we're looking at area, we just look at the surface area of it. We're not looking at the outskirts, so we don't need to really calculate this, but all that it means, so that doesn't mean any difference, because when we looked at perimeter, we had to separately work out the circumference and then add that length. But in this case, all we have to do is work out the area of the half circle. So let's work out the area of a full circle and then halve it. So we go, area is pi r squared, so we go pi is 3.142 times r, in this case 6 squared is 36, so 3.142 times 36 gives us 113.112, and this is for the full circle, so half of it will go 113.112 divided by 2 equals 56.556 meters squared, because we've got meters there. So to summarize, when we looked at the perimeter, it was a case of just going around the shape no matter what, and so all we had to do is work out the perimeter of the shape by adding the sides, and when it was a circle, we'd have to look at the circumference, and a triangle, again, we're looking at the sides that are outside of it, we're not looking at the one inside. Whereas when it came to area, all we did was looked at and worked out the area of the shapes that made the compound shape, the simple shapes that made the compound shape. In this video, we'll learn to use the formula to find volumes and surface areas of 3D shapes, including cylinders. At level 1, we learned how to work out the volume of cubes and cuboids. And if you recall, the volume of a cube or a cuboid was worked out by multiplying length times width times height or depth. So it was 3 dimensions, and our answer was in cubic meters, centimeters, millimeters, and so on. So what I want us to look at first is how to work out the volume in another way, or look at another perspective of working out volume. And to help you with that, I want you to think in terms of what do we get when we multiply length by width? And that is the area. So volume can be worked out by multiplying area times the height or the depth. So we'll show you what that means. So I've got a cube here, and as we know, volume is about how much you can put in or how much space it takes. So I've put in some jelly inside and I've just got it out. So if I cut off the top bit, I can make this into a 2D shape. And what volume is is that surface area repeated so many times. So there are layers and layers of it within the shape. So if I stack them up again, that would make the volume. So that is another way of working out the volume. Another perspective which is going to be very helpful when it comes to other shapes as well, because the same thing applies to cuboids, the same thing applies to cylinders, prisms. Because if I show you this, so this is a cylinder, and as we said, that's the surface area of it, and that surface area, as you can see, if we cut it in slices, would have many of it to make the volume. So this repeats itself throughout. This is what we call also the cross section, because it's the same throughout the height or the depth. So if I get this out and I cut a slice of the circle, the cross section, that is going to be the same again and again. So it's really difficult to show, but the idea is that the same surface area continues throughout the depth or height, and exactly the same thing happens here. So I've got a triangular prism filled with jelly, and this is the cross section, and if I cut slices of this, I'd have many of them throughout the height or the depth. So if I work out the surface area of this and I multiply by the height, then I would have the volume of the shape. And the same thing here, if I work out the surface area of the circle or the cross section, the same, and then multiply it by this length, which we call the height or the depth, then we'd have the volume being worked out. So let's work out the volume of this prism. So if this is 4 centimeters, the base, and the height being 5 centimeters. So the surface area of the triangle first would be 5 times 4 divided by 2. So 5 times 4 is 20, divided by 2 is 10. So I've worked out the surface area of the triangle or the cross section first. So that is 10. Now we said that is being repeated throughout, so we're going to multiply it by this, the length here, or the height. So then it would be 10 times 6 equals 60 centimeters cubed. So that's the volume of the prism. So in other words, to work out the volume of the prism, we worked out the area of cross section, multiplied by height or depth. So that's how we work out the volume of the prism. So if we want to work out the volume of the cylinder, then again we said we work out what is the area of that cross section, and that's the circle here. So the volume of cylinder, again, area of cross section times the height. So area of cross section, how do we work it out? So if the radius is equal to 2 centimeters, then what do? We do pi r squared. So r is 2, 2 squared is 4, so 4 times pi, so 4 times 3.142, and that gives us 12.568. So I'm going to keep it the same there, and then what do? We multiply this area by this height. So if there's 7 centimeters, all I do, get the answer and multiply it by 7. So this gives us 87.976 centimeters cubed. So 87.976 centimeters cubed. So with these shapes that have a cross section which repeats itself throughout, so you have a circle, it continues to be a circle up to the other end, or with a prism here that you have a triangle and it continues to be a triangle up to the other end, same as a cube. So it has a cross section which is the square, and a cuboid which has a square and that is repeated throughout, and we get a square at the other end as well. So with these shapes, the formula of volume is straightforward. Work out the surface area, or the area of the cross section, and then multiply it by the height. What about shapes like a cone or a pyramid? Because they don't have a cross section. We start off with a circle and we end with a point. And the same thing here. We start off with a square and we end with a point. They have both have pointy tops. So what do we do in this case? And this is what we're going to look at now. So we'll try and make that link now between the shapes with a cross section and the shapes that are pointy, like the pyramids and cones. So if I ask you to compare these two, what do you notice in between them? So these two shapes have the same height. So this height from the bottom to the top is the same as the height of this cube. So the pyramid that I have and the cube have the same height, and this area is exactly the same. So they have the same base. The only difference is that, of course, so this is a pyramid and it starts getting smaller and smaller till it becomes pointy. That surface area at the top, at the bottom, the base gets smaller and smaller to come to just a point, whereas that doesn't happen with a cube. So I wonder whether there is a relationship between the two volumes. So if I try and put, because I can see this has a smaller volume, I can see that. So if I try and put the jelly into the cube, how many of these would make a cube? So I'll try and put it inside. So I've put one and it's not filled. So I'll try and put another one to see if that fits and if it fills it up. And as you can see, it doesn't yet. So I'll try one more. And with the third one inside, it makes exactly the volume of the cube. So exactly 3 lots of the pyramid made the cube. So in other words, what we're saying that the volume of one pyramid is 1/3 of the volume of the cube with the same base and the same height. So having the volume of the cube already here, which is length times width times height, or volume of the area of a cross section, volume equals to area of cross section times height, I can say is that the volume of the pyramid is equal to 1/3 of length times width times height. Or the other alternative would be equals to 1/3 times area of cross section times height. So that's the base as well. So this is just to help you, but the reason this isn't an official formula. So if it helps you remember, then use it. But this is the official formula. And this makes more sense because in a pyramid, you really don't have a cross sections, but you have it in the cube. So if you try and make the link between the two, then that's perfectly fine. Now, my next question is this the case when it comes to a cone? So let's have a look. So I've got 3 cones and I've got a cylinder which has the same base. So I'll try and empty these into the cylinder to see whether it is 3 that make the volume of it. So I've done one and there is another one and still not filled. So and that is exactly it. That is the volume of the cylinder. So we can say the same thing for the volume of the cylinder. So I'll put down volume of the cylinder is equal to 1/3 of area of base times height. Now, area of base, what is the base when it comes to a cone? That is the circle. So the circle, we work out the area by multiplying pi r squared. So we can have that instead of area of the base. So let's illustrate with examples. So we have a pyramid, and let's suppose this is 3 centimeters and this is 3 centimeters, and the height is 4. So surface area 3 times 3, which is 9. 9 times 4, which is 36. So 36 then divided by 3, because we said 3 lots of them make a cube. So in other words, is the same as saying 1/3 of 3 times 3 times 4. So that was 9 times 4 is 36. 1/3 of 36 is 12. So 12 centimeters cubed. You could do it with a calculator as well. So 1/3 of, so times 3 times 3 times 4 equals 12, or just do 1 divided by 3 times 3 times 3 times 4, so that still gives us 12. Or you could do 1/3 of 3, which is just 1, times 3 is 3, times 4 is 12. So there are different ways of doing this, and let's have a look at an example of a cone. So we said 1/3 of pi r squared times h, so it got 1/3 of, if the radius of this is, like we said in the previous example, 2 centimeters, so pi r is 2, so 2 squared times h, which let's suppose is 4, so from the base to the top is 4 centimeters. So we could plug this into the calculator, because we have pi, but we could do it ourselves as well. So 1/3, or 1 divided by 3, times 3.142 times 2 squared is 4 times 4. So that gives us 16.7573, that is recurring, but we don't need to continue adding 3's. You can leave it like that, so rounding it, and that the unit is centimeters cubed. So again, when we work out volume, it's cubed because we're looking at 3 dimensions: length, width, height. So now looking at the volume of a sphere, if you check the formula, this resembles 2 other formulas. We can see that 4 there coming from the surface area, so 4 pi r, and that is cubed. And we can see a third there, so that is coming from the formula of cones or pyramids, which is said they start with 1/3 pi r squared times the h, but that's not a different height this time round, because it is radius all round when it comes to a sphere, and we'll have a look at what that means. So in other words, this is saying that there would be 4 circles like these ones that would be filled with pyramids. So we'll actually see what that means in reality. So I will draw around the big orange now. So I've done that now, and I'll try and cut these into small pyramids and place them on top. So I filled the 4 circles with orange pyramids. Obviously it can't be perfect, it can't be really exact because it's just fruit, but I hope it gives you a general idea of what we mean. It helps you remember what the formula is. So I've put the orange pyramids within the circles, within the 4 circles, just like we did with the skin at the top. So it's rather messy, not perfectly exact because we're dealing with fruit, but I hope it gives you the idea. So if we had a sphere with a radius of 3 centimeters, for example, what would we do? So we'd write 4/3 times 3.142, which is pi, times the radius being 3 cubed, because we're dealing with volume as well. So we can do this with a calculator or by hand. I'll just do it quickly with a calculator. So 4 divided by 3, then times 3.142 times 3 cubed is 27. 3 times 3 is 9, times 3 is 27. So that gives us 113.112 centimeters cubed. In this video, we'll learn to use the formula to find the surface areas of 3D shapes. So I've got a cube, cuboid, pyramid, cylinder, prism and cone. So we'll take them in turn to see how we can find the surface areas of them. So surface area is the whole area of all faces all together. So it's a bit like thinking of wrapping paper they'd put around, or skin, or peel. So we'll work out the area of one of these, and apparently a cube has 6 faces, so we'll multiply it by 6 in this case because they're all the same. So if this is 4 centimeters and this is 4 centimeters, then we go 4 times 4 is 16. So this is 16. 16 times 6 . So 10 times 6 is 60. 6 times 6 is 36. So 60 and 36 is 96. So that is 96 centimeters squared. So we're looking at area, and that's why we've got squared. For a cuboid, let's suppose this is 4 and this is 2. So 4 times 2, which is 8. And then we'd have, so this would be 4 as well, and this is 4 as well. So then we go 4 times 4, which is 16. So this is 4 and 4 again, because they are the same. So another 16. And then this one is 2 and 4, because this is 4, this is 2. So that is 8. And this one here is 8. So what is left now is this one, which is again 2 and 4, just like these other faces. So that is 8 again. So we have 2 lots of 16, which makes 32, and we have 4 lots of 8, which is again 32. So that happens to be equal to 64 centimeters squared. So they happen to be the same, 16 and 16, 32, and 4 lots of 8, 32, but it's not always the case. So it can have different values. So all we did was go around and add the areas of all the faces, and there were 6 of them in each case. Now we'll look at the pyramid, square-based pyramid. So if this is 5, then this is going to be 5 as well, and let's say this is 4, so this must be 4 because it is square at the bottom. So we'll look at the face at the bottom, which is 4 times 4, so that is 16, and then we'll need to look at each of these 4 triangles. So I said this is 5 and this is 5, but is that really important when you work out the area of the triangle? So what we need is this perpendicular line here, which forms a right angle with a base. So if I know that this is 4 and this is 4.5, so how do I work out the area? So I go 4 times 4.5 divided by 2, and that gives me one of the triangles. So 2 lots of 4.5 is 9, and another 2 lots is 18. 18 halved is 9, so one of these is 9, but I've got 4 of them. 4 times 9 is 36. So we've got 16 and the 36. 10 and 30 is 40, and the 12 is 52. 52 centimeters squared. And when it comes to the cylinder, what is important, as always with circles, is that we know the radius of or the diameter, either of them. So if this is 2 centimeters, then we can work out the area of this face, and then which is the same as the area of this face. So we've got 2 of them. Then we can work out the area of this other face. So to find the area of the face, I multiply pi r squared, so 3.142 times r is 2, so r squared is 4, so that gives me 12.568, but I have 2 faces that are the same, 2 circular faces, so I'm going to multiply this by 2 to give me 25.136. Now what I need to do is work out the area of this face. So what we need to know is how high this is. So let's suppose it's 4 centimeters, but we could also measure it, or you'd be told, and that is multiplied by this circumference, because this is how long this face is. That's the width and that's how long. So the length of it is equal to the circumference of this circle. So the circumference, so that's 4 times that circumference. The circumference, we said, we work out by multiplying pi with the diameter, or 2 lots of pi times r. So 2 lots of 3.142 times r, which is 2, that gives us 12.568. So that is the length, and the width is 4, so I'm going to need to multiply that by 4 times 4 to give me 50.272. So I've added these two, I've got this. So in total we've got 50.272 plus 25.136. So that makes 75.408 centimeters squared. So what we did, we worked out the surface area of the circle, multiplied by 2 because there are 2 of them, and then worked out the area of this other face. Now we'll look at the surface area of this triangular prism. So again, we can see 3 faces that are rectangular and 2 faces that are triangular. So if this is 4 and this is 2, so we'd have 8, and then this would be 2 and 4, since this is an equilateral triangle. So 2 and 4, 2 and 4. So 8 and 8 and 8. So that is 24 for the rectangular faces. Now the triangular one, so if this is 2 and this is 1.7 for example, so we'd multiply 2 by 1.7 and then half it. So 2 lots of 1.7 gives us 3.4. Half of it gives us 1.7 again, because we multiply by 2 and we halving, so that means we keep the number the same. So 1.7 on this side and 1.7 on the other. That gives us 3.4. So then we add them together to give us 27.4 centimeters squared. And finally, we look at the cone. Cone has a slightly different formula. So with a cone, you'd look at the base, so that is a circle. So we work it out by multiplying pi r squared. So if the radius of this is 2, then pi r squared is going to be 3.142 times 4, which is 12.568. Now we'll need to look at this, the area of this face. In order to work that out, we need this length, or the height, this slanted height here. So that goes a straight line down to the base. So you'd need a ruler to do this. So if that is 5 centimeters, then what we do with it is pi r multiplied by 5. So 5 pi r. So that slanted height is multiplied by pi r. So 5 times 3.142 times the radius, which is 2, gives us 31.42. So that all together, this, which is the surface area of this cone, works out as 31.42 add 12.568 to give us 43.988 centimeters squared again. So this was for the surface area of this face of the cone, but altogether this was 43.988 because we needed to include the surface area of the base. Now if you're interested in why this works, keep watching. So we'll investigate to see why it actually works. So we'll rewrite the formula of the surface area of the cone again, which is pi r squared that was for the base, add, if we call this L, if we denote this slanted height by L as a length, maybe we can say then we work out as L pi r the surface area of this other face. So why is this the case? If we look at this first part for the base, the first part, that gives us the base which we are familiar with. We know how to work out the area of a circle, and that's where it's coming from. So if I am to show it through a net, that's the part at the base, that's the base, that's the face at the bottom. So we'd put this together in order to make a cone, and that goes on top. And what we're interested in to find out is, why is this L pi r? So I want you to recall, where did we find pi r before, or something similar? And what it's close to is 2 pi r, which is the circumference of a circle. So pi r in itself is actually half of this, which means half of the circumference. So this circumference here at the bottom, we're talking about half of it. So to make the full circumference, we need 2 lots of this, or we could halve the full circumference and multiply it by L, which is this slanted height that we talked about. So what I'm going to do is I'm going to measure with a string this circumference of the circle, approximately, which is the same as this one. And what I'm going to do is I'm going to cut it in half. So instead of 2 pi r, which is this one, I'm going to get just pi r and multiply it by L. So I'll cut it in half. So now what I'm going to do is I will draw a straight line based on this, or the same, with the same length. So using a ruler, I will draw a line that is of the same length as the string. So placing it here, just a bit longer. So this is pi r, half of the circumference. What we're multiplying it by is L, which was this length, and in this case that could be anywhere, either here, there, or any of this. So this is exactly L. So I can put L here. As you can see, what I'm trying to do is to create a rectangle. So it would be perhaps better if I do it this way, ensuring that we have a right angle here, and this is where we've got to stop. So what I'm going to do now is cut off this bit. So it's got to be 90 degrees. And I will continue the line to try and meet this other side. So this rectangle that I've created is pi r times L. Now I will cut this bit and try and fit in there. So obviously it's a shape that I've got to play with, but you get the idea, because all these bits would make the whole shape when you put them together. So to summarize, what did we discover? It is that pi r squared works out the surface area of the base, the circle at the base, this one here. L times pi times r works out because L being the slanted height multiplied by pi r, which is half of the circumference, gives us this face. So in other words, if we had a cylinder that has the same base, what we did with the cylinder, we multiplied the circumference by this height. What happens with the cone, you can multiply the circumference by the slanted height and divide it by 2. So I can write here that this is for the cone, whereas for the cylinder we had 2 lots of pi r squared, because we have 2 circular faces, and what we add into that is 2 pi r times h. And that is the difference between them two. I hope this investigation has helped you to look at surface area of the cone and help you remember. In this video, we'll learn to use formula-defined volumes and surface areas, and we'll focus specifically on spheres. So we're looking at the surface area and volume of a sphere. that's the formula for the surface area, so 4 pi r squared, and we know what pi is, 3.142, and r is the radius, so whatever the radius of the sphere, you'd be given that. So all you have to do is multiply. And for the volume, 4/3 of pi r cubed. So if you input this into the calculator or try and work out by multiplying, that is pretty straightforward. But what we'll try and do is see, why does this happen? Why is this the case? Why is it 4 pi r squared? And why is the volume 4/3 of pi r cubed? So I'd like you to have a look at this and see, where have you seen part of this? And pi r squared, as we know, is the area of the circle. So it's 4 lots of the area of the circle, the surface area. So what I've brought here is a tangerine to illustrate. So it's not a perfect sphere, but it's something close, and it's good for illustrating. When we look at surface area, it's about the skin of this. That's what we are after, or something that could wrap this. So the formula, as we said, is 4 lots of pi r squared. But where is that circle here? And I'll show you where it is. So if you cut this in half, this is the circle we're talking about, or this, any of them, because they are exactly the same. So it's 4 lots of these areas that make the surface area, the skin of the tangerine. So what I'm going to do is I'll put this here, and I'm going to draw a circle around it. This is quite juicy, so it's rather difficult to draw around it. So I'd have one, and then another one, and another one, and another one. I will reinforce these once I've drawn around them. So I've gone over the lines again. So I've got 4 lots of the circles. So does that equal the surface area of the sphere? So what I'm going to do is I'm going to peel the tangerine, and I'm going to place the skin over these circles, trying to fill them. So we'll see approximately, because this cannot be very accurate. However, even if we could be more precise, that would still be valid. So 4 lots of the area of the circle makes the surface area of the sphere. Obviously, you can't be very precise, as I said before, but I hope you get the idea that 4 lots of the circle make the surface area. So if the surface area of a sphere is something we need to work out, and then we need to know the radius, of course. We do 4 times 3.142 times 2 squared. So we can input that into the calculator or work it out manually. So 4 times 3.142 times 2 squared is 4. So that gives us 50.272 centimeters squared, because that was 2 centimeters. So it's as easy as that to work out, and we get the link between them two. So now it's easy to remember the formula, where it's coming from. So we'll try and do the same with the volume of the sphere. In this video, we'll learn to calculate actual dimensions from scale drawings and create a scale diagram giving actual measurements. So we'll zoom in and have a look at this question. So we've got to find the actual dimensions of this field, write them in meters. So we've got the field here, and the scale is 1 to 400. So 1 centimeter here will be 400 centimeters in reality. So we'll start measuring to find the dimensions. So this is 4 centimeters. So I'll replace this one with a 4. So to get from this to that, we multiplied by 4. So we need to do the same on the other side. So that would be 1,600 centimeters, which is equal to 16 meters by dividing it by 100. Now we'll have a look at this one, and it is 13 centimeters. So we'll multiply 13 by 400. 4 lots of 10 is 40. 4 lots of 3 is 12. So 40 and 12 is 52. Adding the 2 zeros is 5,200 centimeters, which is equal to 52 meters. This is 7 centimeters. So 7 times the 4, 28, add the 2 zeros. That gives us 28 meters. This is 8 centimeters. So 32 meters. Now we can work this out. It could be a case of 52 take away 32 in this case. So it's 20 meters, or you could measure it, and this is 5. So 2,000 centimeters, which gives us 20 meters. And similar thing here, we could take away 16 from the 28, or the other thing we can do the other way is 3 times 4, and that gives us 12 meters. So we've worked out the actual dimensions. The question is, a rectangular football pitch measures 120 meters by 55 meters. Create a scale diagram for the football pitch. So it is rectangular, so we know it's gonna look like a rectangle with one of the dimensions being longer than the other one. So there's going to be length and width. And looking at the size of the paper, length would be along here and then width on this side. So we've got 120 meters, so we're going to try and fit 120 meters long here, but of course that's not possible, so we're going to have to use a scale. We're going to scale this down, but what to, and we need to decide that. So what I'm going to check is how many centimeters long this is. So we've got 15 and about 5, which makes 20. So I think I'm going to do, because I can fit 12 centimeters here, so that would mean dividing this by 10, which in other words means that 1 centimeter on the diagram will probably be 10 meters in reality on the ground. So let's try that out. So if I draw the length of the football pitch being actually 12 centimeters, so if this is 12, that means 1 centimeter will be equal to 10 meters on the ground. And on the other side, following the same scale, then we're going to have to divide this by 10 to get 5.5 centimeters. So that's going to be around here. And we'll do the same on the other side as well. And we'll connect these two dots. So let's check that now. We could write the scale as 1 centimeter to 10 meters. Let's have a look. Does that work? So I've got 12 centimeters here. 12 times 10, because 12 centimeters will be, so to get from 1 to 12 we multiply by 12, so 10 times 12 is going to be 120 centimeters. So this was centimeters on this side, but on the other side we've got meters, so that cannot stay as centimeters. So whatever unit you have on that side, that's what you're going to keep having at the bottom as well. So on this side we have meters, so we're going to have meters as well. So 120 meters, and that's exactly what we had here. And the next one, we've got 5.5 centimeters, which is matching centimeters. So to get from 1 to 5.5, we've multiplied by 5.5. So if I multiply the 10 by 5.5, it gives me 55. And what is the unit? Is meters. So that matches this one as well, suggesting that we've drawn the scale diagram accurately. Another way we could have written the scale would be this. So we have 1 centimeter to 10 meters. So if I rewrite this to 1 centimeter and convert this to centimeters as well, so that is going to be 1,000, because 1 meter is 100, so 10 will be 1,000. So since these are the same units, I can just rewrite this as 1 to 1,000, and it will be exactly the same as what we had here. So either way, either of these two scales would be correct. In this video, we'll learn to use coordinates in 2D, positive and negative, to specify the position of points. What I have in front of me is a plane. This is what we call a plane. Now what this resembles is number lines or thermometers, where you start with positives and they go down to negatives, and same thing across here. What we call this horizontal line is the x-axis. And what we call this vertical line is the y-axis. So this also resembles the graphs that you've been using when showing data or representing data in it. You normally use this part of the graph where you'd have sometimes time at the bottom and you'd have the numbers going up. So what this is an extension of that with negative numbers as well. So what we're going to do is we're going to plot some points. I want to plot a point that is 1, 1. What does that mean? So the x comes first. So first of all, we decide horizontally where we'd go, where we'd stop. Shall I stop at 0, 1, 2, minus 1, minus 2, minus 6? Where do I stop? So that's the first thing I do. And the first number within the brackets tells me that. Stop at 1. So there we go. I need to stop here. Then do I stay here? Or do I go up or do I go down? So where do I stop next? This time vertically. And that's what the second number tells me. It says 1. So I'm going to be within this line, but do I go to 1 or minus 1? That's saying just 1, positive 1. So I need to go there. As you can see, the x is equal to 1 and the y is equal to 1, just like this is saying. So this is what we're going to call point A. So let's label that. Now let's have a look at another point. Let's make or plot point B at 5, 3. So again, horizontally first, we stop at 5, and then that means we're going up 3. So we're going to this point, y being equal to 3. So this is point B. Let's have a point C, which I will put down as 4 minus 2. So 4 horizontally, I'll stop at 4, but I'll go to minus 2. Yeah, so 4 minus 2. So this is point C. There is minus 2. Then let's have a point D at minus 4, 3. So there's 4, but we need to go to minus 4 and then 3. So we're going up to 3. So this is point D. And point E at minus 5, minus 2. So we're going to minus 5 and then minus 2. So this is point E. If I give you a point, let's say a point G will be here. What are the coordinates of that point? Find the coordinates. So again, there is a point. We'll start with the horizontal line first, the x-axis. So where are we stopping? That's minus 3. and then going up to 2. So that's the y-axis. -3, 2. Let's have a look at this point here. What are the coordinates of that point? So x-axis, that's -2, and y is -3. So -2 -3. And one more. Let's have a look at this point here. So that's 2 -4, so 2, -4. So this is how you use coordinates in 2D, positive and negative, to specify the position of points. In this video, we'll learn to understand and use common 2D representations of 3D objects. So what you have in front is 2D representations of 3D shapes, which resemble 3D objects like boxes, maybe ice cream cones, maybe balls. So this here is a cube, and so is this one, and we have cuboids over here, cones, pyramids, cylinders and spheres. So just by looking at them, we should be able to know where are the faces. So which ones are the faces? And we know these are the faces of the cube. And where are the corners or the vertices? And also the edges. So, or the bases, where are the bases? By looking at them, we should be able to identify them. So if we're given dimensions, we should be able to work out surface areas or areas of faces or volumes. So if we're given that this is 1 centimeter, then we know that this is going to be centimeter and this 1 centimeter and so on, because this is a cube. So we can deduct the volume through this, which has got to be 1 centimeter cubed, or we can work out the surface area because we know there are 6 faces in here, and each and every one of them is 1 centimeter squared. So that must be 6 centimeters squared overall. And the same thing, if we're given the radius, we should be able to work out the volume of the cone, and if we're given here the radius as well, maybe the surface area, maybe the volume. But at this level, we're given the formulas for this. So that shouldn't be a problem. Or when it comes to the cuboid, if we're given the dimensions, we should be able to work out the surface areas, we should be able to work out perimeter of certain faces, or the area of certain faces, or the volume. We can also find the lines of symmetry, because we know that this is halfway through this phase, so this must be halfway through. So this cuts the shape in half, or this one here, for example, this one here as well. So this helps us a lot because these resemble 3D shapes that we see in everyday life. For example, shapes of houses or sheds or maybe gardens. And that can help us with planning. Say, for example, if we've got a drawing or a diagram of a house maybe, or a shed, we should be able to work out what is this area here. For example, if we're given the dimensions, let's say this is 4 meters, this is 3 meters, so there must be 12 meters squared. There's also to plan views and elevations. So if a top view or plan view of a garden, it looks like this, so you know that it's going to be 2.5 meters this side and maybe 5.5 meters, then you can work out the fencing, or you could work out the surface area as well, the area that this covers, which helps with how much grass you're going to need to cover the area or to put fencing around as well. In this video we'll learn to draw 3D shapes to include plans and elevations. In another video at level 1 I've looked at plans and elevations of simple 3D shapes. Now in this video I'll look at 2 compound shapes. So I've made them using 2 cuboids. So we'll take them in turn. So you'd have a picture of this, for example, given to you, of this 3D shape. So a plan is what you can see from the top. And we have 2 elevations. We have the front elevation, which is what you can see from here. And we have the side elevation, which is what you can see from here. So we'll draw these together. So what you can see from the top is 1, 2, 3, 4, 5, 6 units going across. You'd need to use a ruler, but I don't for simplicity in here. And then we go 1, 2 down, and then 1 across again, 1 up, 1, 2, 3, 4, 5 across, and 1 up. So this is what you see if you turn it this way. This is called the plan for this shape. Now we'll do the front elevation of the shape. So front, another way to look at it is like more to the left. So front is to the left and the side elevation is to the right. So what can you see? I can see a square of 2 units by 2 units. And now with the side elevation, so if you turn it this way, this is what you'll be able to see. So 1, 2, 3, 4, 5, 6 units across and 2 units down. This is the side elevation. So we'll turn it to its original position again, and we'll look at these once more. So these are the plan and the side and front elevation for this shape. We'll now look at the other shape. So we're given this position. This position is really important. You can't see what is behind here or there or underneath. So you can see only 3 views. You can see from the top, which is the plan. And you can see from the left, which is the front elevation. And you can see from the right, which is the side elevation. So looking at the plan, I can see 1, 2, 3, 4, 5 units going across. And then we have 1, 2, 3, 4 going down. You'd need to use a ruler and be more precise than I am been. So we go 3 up, then across. So this is the plan of this shape. Now the front elevation, this is what we can see. So 1, 2, 3, 4, 5, going down by 3, 1, 2, 3. And the side elevation, 1, 2, 3, 4, 1, 2, 3, down. If you're not given a grid or dotted paper, then you'll have to do this on normal paper, but you have to use a ruler and the actual measurements. In this case, each and every one of these cubes is 1 centimeter, so I'd have to draw them being 1 centimeter on paper. In this video, we'll learn to calculate values of angles and or coordinates with 2D and 3D shapes. So the first thing that we'll start with is with a triangle. So how many or what do all the angles of a triangle add up to? And for that reason, I've got a triangle here and I'm going to mark all of its angles. And what I'm going to do, I'm going to tear it to bits. So I have 3 parts and I'm going to put together these 3 angles of it that I marked. And as you can see, it adds up to 180, which is a straight line or half of a circle. So that is a very important thing to remember, 180 degrees. If you ever forget, kind of cut up a triangle and put all of its angles together. So based on that, if we have a triangle that has 90 degrees on one corner, and we've got, let's say, 30 degrees, so the other one must be 60, because 90 and 30 and 60 makes 180. So you're given 2 of the angles and you'll find the third one, because all of them add together to 180. And that helps us because if we split any of these shapes into triangles, that means that we can have 180 here and 180 there. So this adds up to 360. So if you're given 3 of them, you can work out the next one or what is left. And same thing here, so you can cut this into 2 triangles, 180 here and 180, so this should add up to 360. And same thing over here, 180 and 180 and 180, and same with all of these. So the key thing to remember is that the angles within a triangle add up to 180. But it's also worth remembering that a square has equal sides which are parallel to each other. So same thing when it comes to the parallel sides of a rectangle. So if we're given a plane and we're given 2 dimensions of a rectangle, we should be able to work out the coordinates or the other 2 dimensions of the rectangle. So since this is 1, 2, 3 units long, I'm going to go 1, 2, 3, and it's going to be parallel to this. So it's got to be this coordinate here, 4, 4 for this corner there. And I can just join these 2 and it is 1, 2 units wide as well. So that helps me with plotting, finding the coordinates and with the angle. Now linking 3D shapes with coordinates and angles. So if this was showing maybe a room from this point of view, you could extend this to show this side or this wall. So this has got to be parallel to this, and we would know that although it doesn't look like this, in reality would be 90 degrees, because we know the properties of rectangles, and a wall is the shape of a rectangle. So this is going to be 90 degrees, and this is going to be 90 degrees, and this is going to be 90, and so on. So that's, although it doesn't look like, that's what it's going to be like. And this is going to be parallel to this one, and this is going to be 90 degrees, and so on. So again, we extend this to make it parallel to the other side, and this is parallel to this side, and this, of course, 90 degrees, and now this has got to be parallel to that, and it's going to be of the same length, and we make this to parallel to that other side. Obviously this needs a ruler and of course a protractor to measure the angles. So this is going to be perpendicular, so we know this is going to be 90 degrees. So I've just drawn a cuboid in there, and it's the shape of a room as well. So based on this, you can continue with the roof. And by knowing these two angles, you should be able to work out what this angle here is as well. And you know that this is 90 degrees and this is 90, and so on. So we're using the knowledge of the 2D shapes when it comes to working with 3D shapes. So whatever we learned about the angles of a triangle, which add up to 180 degrees, we can use it here. So if this is 60 and this is 60, this is going to be 60 as well, because they all add up to 180. In this video, we'll learn to calculate the median and the mode of a set of quantities. We've looked at the mean and the range before. Now we'll focus on the median and the mode. As you can see here, median refers to the middle value, so putting them in order and finding the middle value. And mode is the most common value, the one that repeats itself most. So we'll start with the median of these values. So these are the scores out of 10 in a maths test for a class. And what we're going to do to work out the median, we're just going to put them in order from the highest to the smallest, to the lowest, or from the lowest to the highest. It doesn't really matter. I'll just go for the highest to the lowest. So I can see the highest one is 8, and then I've got 7. There are 2 7s, so I must make sure I write both of them. Then we've got a 6 here, 6, 6 and 6, and we've got a 5 and a 5, then a 4, then a 3, and then a 0. So these are in order. Let's find the middle value, the one that sits right in the middle. So crossing out both sides, one each side. And I can see there is a 6. So this means that the median for this set of values is equal to 6. Now let's look at these ones. So this is spending for a week for somebody. So we'll find the median of the spending. Again, putting them in order. The highest value out of all of these is the 25. So we'll write 25, and then we've got the 21. Then we've got £18.50. Then we've got the 17, £15.10, and 14 finally. So crossing them out both sides, we've got these two values in the middle. So what are we going to do now? We're going to add them together and divide by 2. So 1850, add the 17, gives us 35.50, and dividing this by 2 now gives us £17.75. So this is the median for this set of quantities. Now the mode is the most common value, the one that repeats itself most. So if I have a look at these, I've got 2 7s, but I've got 1, 2, 3, 4 6s. I've got 2 5s as well. So I've got more 6s than I have 5s or 7s. So for this case, the mode is equal to 6 as well, just like the median for this set. Now looking at this, is there any value that repeats itself? No, all of these are unique, they don't repeat themselves. So in this case, we haven't got a mode. So no mode for this set of values. So to summarize, median, we put them in order, smallest to the largest or largest to the smallest, and find the middle value. If there is an odd number of values like we had here, you can just easily find that, spot it by crossing numbers out from both sides, and that was a 6. If there are 2 numbers in the middle, then we add them together and divide them by 2, just like we did in here. When it comes to the mode, we're finding the number that repeats itself most, and that was 6 again here, because we had 4 lots of 6. And sometimes there is no mode, so there is no number in the set that repeats itself, and in that case we just write no mode. If there is no mode for a set of quantities, please don't write mode equals to 0, because that can be a value in itself, just like we have it here. So if I write here mode equals to 0, that means there would be perhaps 2 zeros. So 2 of the days this person would spend £0, or 3 of the days, or 4 of the days, and so on. So please just write no mode if there is no mode. In this video, we learned to estimate the mean of a group frequency distribution from discrete data. So what is discrete data? Discrete data is data which has specific values. Like an example would be size of clothes. You could only have sizes such as 6, 8, 10, 12, 14, 16, 18, and so on. So you can't have a size 11.2, for example, but you could have height being 183.5 centimeters. So height in this case is the continuous data, and the size of clothes is discrete data, so specific values when it comes to discrete data. The example that I have here is the marks that have been received by a group of students. So we've got 7, 6, 6, 6, 4, 2, 3, 5, 6, 8, 7, 5, 3, 0, 5, 6, 9. So this table tells you that you failed the exam if you scored between 0 and 4. You pass if you score between 5 and 6, or 5 and 6. You get merit if you score 7 or 8, and distinction if you score 9 or 10 marks. Now we'll see what this means. Frequency is how many of these marks you'd see in the class. So looking at fail between 0 and 4, we've got a 4 here. So there is 1, 2, 3, 4, 5. So there'll be 5 fails. And between 5 and 6, so we've got 1, 2, 3, 4, 5, 6, 7, 8. Merit, we've got 1, 2, 3. And distinction, we've got only 1. So normally when you work out the mean, you'd have specific values. So in this case, between 0 and 4, it's a range of values. We have 0, 1, 2, 3, and 4. But we're going to find the mid value. So as I said, it's 0, 1, 2, 3, and 4, all included. So in the middle is the 2. So we're going to find that mid value or midpoint. And between 5 and 6, we've got only 5 and 6, so it's going to be 5.5. Between 7 and 8 is 7.5. Between 9 and 10 is 9.5. So if you're not given the number of marks, but you just have this table, and you'd be told that 5 learners received a fail, you don't know then whether they got 0, 1, 2, 3, or 4 marks. So that's why we find a midpoint, and we multiply it by that mid value, or that midpoint, which in this case is a 2. So 2 lots of 5 is 10. 8 lots of 5.5 is 44. 3 lots of 7.5 is 22.5. And 1 lot of 9.5 is just 9.5. So we'll add all of these together. So we have 10, 1 carried over, 1 and 4 is 5, and 9 is 14, and 2 is 16. 1 and 1 is 2, and 4 is 6, and 2 is 8. So it's 86 the total. But we still need to divide this by how many values we have. So we have 86 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And this gives us 5.059. And this is an estimate of the mean of the grouped frequency distribution from discrete data in this example. In this video, we'll learn to use the mean, median, mode and range to compare two sets of data. So I've got the marks for the same tests from two different classes. And as you can see, I've written class A in blue and class B in green to differentiate. And now I've worked out the mean for each class, the median, mode and range. Now we'll use these to compare them. So as you can see, class A on average scored 4.8 marks, whereas class B 5.6 marks. So what does that tell us? Since this is an average measure, the mean, that tells us that class B did better in general. Class B did better on average. That's a better word to use. And the median as well does about the average as well. So that is supporting the same thing, that class B did better on average because they received on average 6 marks, whereas class A 5.5 marks. So again, this supports the same thing, that class B did better on average. In terms of the mode, which is the most common value, the most common mark. This shows again that the most common mark for class B was 7, which was 1 mark higher than for class A, yeah. So in terms of the mode, we can say that the most common mark was higher in class B. So that again supports the argument that class B did better. And in terms of the range, which we know is the difference between the highest and the lowest mark, that kind of measures the spread. How spread out are these marks? And as you can see from class A, the lowest mark was 1 and the highest was 8, but that was exactly the same for class B. The lowest mark was 1 and the highest was 8. So the spread is equal for both classes. So this last bit hasn't given us much information really. There wasn't a difference between them two, so we can't really properly compare, but at least that shows that that spread was the same. It wasn't the case that the mean was affected by, let's say, a mark that started on 3. So maybe starting with a mark of 3, that would have impacted the mean, that would have impacted the median as well. So having the same range reinforces these other measures that we're using to compare the data. In this video, we'll learn to work out the probability of combined events, including the use of diagrams and tables. So I've got 2 objects. I've got a spinner and a coin. We should be okay to work out the probability of getting 1 in the spinner, or 2 or 3 or 4, and the probability of each of them is a quarter. And with a coin we can get head or tail, so the probability of getting head is half and the probability of getting tail is half. So what we'll look at in this video will be the probability of combined events, so events from both of these two. For example, what's the probability of getting a 3 and tail? What's the probability of getting a 2 and heads? So what we're looking at this time around is independent events, because combined events can be dependent and independent. Why are these independent? Because whatever you get with a spinner does not impact what you get with a coin. We'll later on look at the dependent events. So starting off with these two. What could I get with a spinner? What are the possibilities? I could get a 1. So if the spinner lands on 1, that's what I would have. So I would have 1 and then maybe heads, or 1 and tail. They're both possible. So with a 1 on the spinner I could have then a head or a tail here, and these are 2 possible events. And then if I get 2 with a spinner, I could have heads with the coin, and I could have tails as well. So any of them 2 are possible. And of course, if the spinner lands on 3, I could have 3 and heads, or I could have 3 and tails. And if the spinner lands on 4, I could have 4 and heads, and I could have 4 and tails. So any of them are possible. So as you've just seen, we've looked at all the possible outcomes for both of these two. And what we call this is a listing. And in fact, it's systematic listing, because we looked at each outcome here. That would be a 1. And then we looked at the possibilities for the coin as well. And there were 2. So 1 and head and 1 and tail. 2 and head and 2 and tail. 2 and head, 3 and head and 3 and tail. 4 and head and 4 and tail. So we looked at them in turn. And that's what we call systematic listing. Now there are other ways we could have worked this out, and I'll look at those both. So the possible outcomes for the spinner would be getting a 1, 2, 3 or 4. These are the only possibilities. And for the coin, it's either heads or tails. So on one side, one of the objects, and on the other side, the other object. So I could have 1 if I spin the spinner first. I could have a 1 and heads, or I could have 1 and tails. I could have 2 and heads, or 2 and tails. 3 and heads, 3 and tails. 4 and heads, 4 and tails. And that matches exactly all these outcomes that we have here. Now, the other way we could show the same thing would be through a tree diagram. This is a two-way table. This was listing. Now we'll look at the tree diagram. So it looks like branches of a tree. So let's start off. What are the possibilities for the spinner? What could we get? There are 4, and we could have a 1, 2, 3 or 4. If we get a 1, what could we get with the coin? We could get either heads or tails. If we get a 2 with a spinner, what can we get with a coin? Heads or tails. If we get 3 with a spinner, we could get heads or tails with a coin. And if we get 4 with a spinner, heads or tails with a coin. So these branches show us exactly the outcomes. So we could get 1 and head, we could get 1 and tail, 2 and head, 2 and tail, 3 and head, 3 and tail, 4 and head, and 4 and tail. So that's exactly 8 different outcomes, just like we had in listing and the table. Now through this, it's very easy to work out the probability of combined events. If I want to find what is the probability of getting a 3 and heads, then I could go, okay, where is 3 and heads? That's where it is. So I could go, right, that there is only one outcome like that has 3 and heads. So that would be 1 out of the 8. So the probability of getting 3 and heads is 1/8. Or what is the probability of getting even numbers? Okay, either here or here. So I'd go, where are the even numbers? We got 2h there, so the 2 is the one that we're looking at. The h or t does not matter. And then we've got a 2t, we've got a 4h and a 4t. So obviously this is 4 out of 8 possible outcomes. So 4 out of 8, which is the same as half. So probability of getting even numbers is half. And probability of getting odd numbers then would be again half, because all the different outcomes add up to 1. So that's a half, so you need another half. And if the numbers are not even, they're going to be odd. So half and half gives a whole. So that is equal to 1 as a decimal, or 100% as a percentage. Or I could work out the probability of getting heads. What's the probability of getting heads? We've got 1 head there. 1, 2, 3 and 4. So this is supposed to be a tail, because we've got 2t there, so there are 4. So that is 4 out of 8 again, so that gives us half. So probability of getting heads is half. So the probability of getting tails must be half as well, because the 2 halves make a whole, and that's the only 2 outcomes that we have for the coin. So to summarize, for the independent events, we use systematic listing to show all the different outcomes. We use the two-way tables as well, and the tree diagram as well. We'll now look at the probability of dependent events. So we've got a spinner here. We'll spin it twice, and we'll look at all the different possibilities. When we spin it the second time, we shouldn't get the same number that we had the first time around. So if I got a 1 the first time round, I can't have a 1 the second time round. So that wouldn't be accepted as an outcome. So what that means is that if I get 1 the first time, then I could get a 2 the second time. So a 1 and I could get a 3 second time, a 1 and then I could get a 4 the second time. So I can't have 1 and 1. And if I get a 2 the first time round, I can get a 1 the second time round. I can't have 2 and 2, so I'm going to have 2 and 3, and I'm going to have 2 and 4. And if I get a 3 the first time round, I would get a 1, 3 and 2, 3 and 4. And 4, 4 and 1, 4 and 2, 4 and 3. So these are the possible outcomes. I've listed them. Now we'll look at a two-way table to represent the same information. So let's have first spin. We could have a 1, 2, 3 or 4. And the second spin, we could have a 1, 2, 3 or 4. So now we can draw the table. So if I get 1 in the first spin, and 1 in the second spin, that's not allowed, so I'll circle it to denote an impossible outcome, because that's the rules of the game. And if I get a 2, I can have a 1, get a 3, I can have a 1, 4, I can have a 1. So then 1 and 2 is perfectly fine. 1 and 3, 1 and 4. And 2 and 2, obviously that's not allowed in the game. 2 and 3, 2 and 4, 3 and 2, 3 and 3, 3 and 4, 4 and 2, 4 and 3, 4 and 4. So we've shown in this two-way table what are the possible outcomes. You could highlight these or cross them out to show that they're not possible. And we'll use now a tree diagram. So with a spinner, we could have 1, 2, 3, or 4. Now, if we get 1, we won't allow a 1, so I won't even do that. We can have a 2, we can have a 3, we can have a 4. If we get a 2, we can have a 1, we can have a 3, we can have a 4. If we get a 3, we can have a 1, a 2, and a 4. If we get a 4, we can have a 1, 2, or 3. So with a tree diagram, we have the possibility to adjust them, so we don't include all the numbers. So we could have a 1 and 2, 1 and 3, 1 and 4, 2 and 1, 2 and 3, 2 and 4, 3 and 1, 3 and 2, 3 and 4, 4 and 1, 4 and 2, and 4 and 3. So these are the possible outcomes using the tree diagram. Now we could answer probability questions through this. So, for example, what is the probability of getting even numbers only? So, all the even ones. So we go 2 and 4 is 1, because 2 is an even and 4 is an even, and 4 and 2. So that is 2 possible outcomes out of 1, 2, 3. 3 times 4 is 12. So 2 12s, which we can simplify to make 1/6, because both of them can be divided by 2. And another question, so what's the probability of at least one of the two numbers being bigger than 2? So at least one of them. That's not the case. That is the case, because 3 is bigger than 2, and that is the case. That's not, this is, this is, this is, and this is, this is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 out of the 12 that we had. So we don't include the crossed out sections. 10 out of the 12. Can this be simplified further? We could divide by 2, so that gives us 5 and 6, so 5, 6. So a final question, what's the probability of both of the numbers being the same? Now we said it was part of the game, or rule of the game, that we didn't have numbers that are the same. So that's why when we got to 1, we didn't allow to have a second one. So for that reason, we don't really have two numbers that are the same in one outcome. So that probability is 0 or impossible. In this video, we'll learn to express probabilities as fractions, decimals, and percentages. So I've got 3 different objects in front of me and I'll work out different probabilities. I'll start off as a fraction because that's the easiest one to work out initially. So I want to work out the probability of getting heads in a coin. So the 2 different outcomes that I could have is either heads or tails. So heads is just one of them out of the 2. Now that's written as a fraction. As a decimal, 1 divided by 2 gives me 0.5, which is the same as 50%. And the probability of getting a 3, for example, in the spinner is 1 out of 4, or 1/4, because it's one of the possible 4. So 1 divided by 4 gives us 0.25, and that is 25%. The 2 digits after the decimal point. And finally, we've got the spinner, which has 8 equal sections. The sections are either red, blue, green, or white. I want to work out the probability of getting red. So there is a red here, here, and there. So there are 3 reds. 3 reds out of 1, 2, 3, 4, 5, 6, 7, 8 out of 8. And we're told here as well 8 sections, 8 equal sections. So what I do now is 3 divided by 8, which gives me 0.375. So that's as a decimal. As a percentage, we've set 2 decimal points after the decimal point, 2 decimal places after the decimal point. So that makes it 37.5%. It's like how many pennies you'd have if this was money, if you had a pound sign in front. So really, expressing probabilities as fractions, decimals, and percentages is no different from converting fractions to decimals or percentages. The first thing to do is work out what are you looking at working the probability of. How many is that out of the total? And then pick it from there to express it as a decimal and then as a percentage. In this video, we'll learn to draw and interpret scatter diagrams and recognize positive and negative correlation. So I've started the process of drawing 2 scatter diagrams. In the first one, I'm trying to show the correlation or relationship between weather temperatures and ice cream sales. So I've got some data, and based on that I'll plot those points. So when the temperature is about 2 degrees Celsius, then ice cream sales are quite low. And then as the temperatures set to increase, so do the ice cream sales a bit. So I'm going to show that. So when the temperature is about 8, then perhaps 40 ice creams are sold. When the temperatures go up, so do the ice cream sales. So maybe at 14 degrees, 15 ice creams are sold in a shop. So 24 degrees, maybe 60, 27 degrees, we've got maybe 90, 30 degrees, 100. So what you can see is that when temperatures increase, so do the ice cream sales. So as we said, when temperatures were about 2 degrees Celsius, that was matched with ice cream sales of under 10, so very few sales. And then when the temperatures increased, let's say went to about 16 or 17 degrees, then ice cream sales went up to about 55, and when the weather temperature was about 30 degrees, we had 100 ice cream sales. So that shows a positive correlation, a positive connection, a positive relationship between weather temperature and ice cream sales. Now, on the other hand, I've got here a scatter diagram which I've started but haven't finished, and this is about showing the connection between weather temperature and tea sales, so hot tea, hot drinks. So when temperatures are low, we have very high tea sales because that's quite common. The colder it is, the more likely people are to buy hot drinks. And then as the temperatures increase, we have the tea sales dropping because naturally people are inclined to buy cold drinks or ice cream. So as you can see, when temperatures were cold, were low, tea sales were high. As the temperatures actually increased, tea sales dropped. So increase in weather temperatures, drop in sales. The two opposite words. Here we had increase in temperatures, increase in sales, so both of them go in the same direction. So that is a positive relationship, positive correlation. Whereas here we've got an increase and a decrease. So that means this is a negative correlation between weather temperature and tea sales. I'll show through another example for you as well. So we've got very similar to the first one, we've got a positive correlation here. So one increases, the other increases as well. So that is a positive correlation. And we've got a negative correlation just like this one here. When one increases, the other decreases. And what this is here is no correlation. So you can't really see kind of a line either going upwards or downwards, but we've got some scattered points, scattered dots around the graph. So that shows that there is no clear correlation between the two variables. So this actually shows two things that are not really related to each other. For example, the number of hours you spend swimming with your results in a maths exam, nothing related. Whereas here it could be another example, such as the number of hours you spend revising with your results in a math exam, and a negative correlation could be between you spending time on PlayStation, playing games online perhaps, and your maths exam results.